Somewhere between the orbits of Earth and Mars, tumbling silently through the emptiest darkness you can imagine, there is a rock the size of a small mountain. It is blacker than charcoal, blacker than asphalt. Its surface reflects less than 4% of the sunlight that touches it, making it one of the darkest objects ever visited by a human-made spacecraft. And buried inside that rock, inside grains of dust older than the sun itself, scientists found something that should not have been there. They found the ingredients of life. Not metaphorically, not poetically, literally. Amino acids, the same molecular building blocks that make up every protein in your muscles, your blood, your brain. They were sitting inside a chunk of space debris that has been drifting through the void for 4.5 billion years. And when scientists in a laboratory in Japan cracked open the tiny capsule containing those grains and ran the first chemical analysis, the room went silent. Because the implications of what they were looking at were not just significant, they were civilization-altering. The rock is called Ryugu. It is named after a mythical underwater palace from Japanese folklore. A palace at the bottom of the sea, where a fisherman was said to have discovered that time moved differently than on the surface. The name turned out to be strangely prophetic, because when the Japanese Space Agency sent a spacecraft 300 million kilometers across the solar system to collect a handful of dust from Ryugu's surface, what came back was not just a sample of an asteroid, it was a sample of the past, a fragment of the original cloud of gas and dust that collapsed to form our entire solar system, preserved in a condition so pristine that it predates every planet, every moon, every ocean, and every living cell that has ever existed on Earth. And that sample changed everything we thought we knew about where we come from. The mission that retrieved it, Hayabusa 2, built and operated by the Japan Aerospace Exploration Agency, is one of the most ambitious robotic space missions ever flown. It launched in 2014, arrived at Ryugu in 2018, and spent 16 months in orbit around the asteroid, mapping its surface, deploying rovers and landers, and executing 2 separate touchdowns to collect samples. During one of those touchdowns, the spacecraft fired a copper projectile into the surface at 2 kilometers per second, blasting open an artificial crater and exposing material that had been buried beneath the surface for potentially billions of years. It then descended near that crater and collected a second sample from the freshly exposed subsurface material. No spacecraft had ever done anything like this before. For decades, scientists assumed that the raw materials of life, the amino acids, the organic molecules, the water, were forged here on Earth in volcanic vents or shallow pools battered by lightning. That was the story. Life emerged from chemistry, and that chemistry was local. But Ryugu's dust told a different story. It told us that those ingredients were already floating through space before our planet even existed. It told us that the building blocks of biology are not rare, not special, not unique to Earth. They are woven into the fabric of the cosmos itself, carried from star to star on the backs of ancient rocks. And it gets stranger, because Ryugu is not a solid object. It is a pile of rubble, a loose collection of boulders and gravel, barely held together by its own feeble gravity. If you could stand on its surface, you would weigh less than a paperclip resting on a kitchen scale. You could jump and never come back down. This thing is not a world. It is a ruin, a shattered remnant of a much larger body that was destroyed billions of years ago. And yet, somehow, within that ruin, the most delicate organic molecules in the known universe survived intact. How? How does something so fragile endure for so long in a place so violent? By the end of tonight, you are going to understand how a single space mission, launched from a small island in southern Japan, travelled across the inner solar system, touched down on a spinning diamond-shaped asteroid twice, fired a copper bullet into its surface to blast open a crater, collected samples from beneath the exposed rock, and then flew home carrying less than 6 grams of material that rewrote the origin story of life itself. You are going to understand why Ryugu was not what anyone expected, and you are going to understand what that means for the biggest question humanity has ever asked: are we alone? Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, Let us begin. The darkness of space is not empty. It only looks that way. Between the planets, between the stars, between the galaxies, there is material. Dust so fine that a single grain is 1,000 times thinner than a human hair. Gas so tenuous that a cubic meter of it contains fewer atoms than a cubic meter of the best vacuum achievable in any laboratory on Earth. And within that material, chemistry is happening. Slowly, patiently, over millions and billions of years, atoms are finding each other, bonding, forming molecules, building complexity in the most hostile environment imaginable. Carbon links with hydrogen, oxygen bonds with nitrogen. Simple molecules combine into less simple ones. And somewhere in that process, in that impossibly gradual accumulation of molecular complexity, in the freezing dark, the foundation of everything we call life is being laid, not by intention, not by design, by physics, by the relentless, indifferent creativity of atoms obeying the laws that govern their behavior. Ryugu is a snapshot of that process, frozen in time, sealed in stone, preserved for 4.5 billion years. And reading that snapshot has changed what we know about the deepest question any conscious being can ask. To understand why Ryugu matters, you first need to understand what asteroids actually are. Not the Hollywood version, not the planet-killing mountains of iron hurtling toward Earth in a blockbuster film. The real version. Because the real version is far more interesting and far more important. 4.5 billion years ago, there was no solar system. There was no sun, there was no Earth, there was only a cloud, a vast, cold, slowly rotating cloud of gas and dust, stretching across light years of otherwise empty space. This cloud was made of hydrogen, helium, and something else, heavier elements forged in the cores of stars that had already lived and died long before our corner of the galaxy existed. Carbon, oxygen, silicon, iron, nitrogen. The ashes of dead suns scattered across the void by supernova explosions, mixing with primordial gas that had existed since the first few minutes after the Big Bang. And then something disturbed the cloud. Perhaps a shockwave from a nearby supernova. Perhaps the gravitational nudge of a passing star. Whatever it was, the cloud began to collapse inward. As it fell, it spun faster, the way a figure skater spins faster when she pulls her arms in. The center grew denser and hotter, and eventually, at the heart of that collapsing mass, temperatures reached 10 million degrees. Hydrogen atoms began to fuse into helium, and a new star ignited, our sun. But the sun did not consume everything. A disk of leftover material, dust and gas, continued to orbit the newborn star, swirling like water circling a drain. And within that disk, something beautiful and violent began to happen. Tiny grains of dust, some no larger than a grain of sand, began to collide and stick together. Static electricity held the first clumps. Then gravity took over. Clumps became pebbles. Pebbles became boulders. Boulders became mountain-sized bodies called planetesimals. And planetesimals, crashing together over millions of years, became planets. This is the standard story. You may have heard it before. But here is the part most people miss. Not all of that original material made it into a planet. Some of it got left behind. The reason is Jupiter. Jupiter formed fast, faster than any other planet in the solar system. Within perhaps 3 million years of the Sun's ignition, Jupiter had already accumulated enough gas to become a giant, a body so massive that its gravitational influence dominated the inner solar system. And Jupiter's gravity was not gentle. It stirred the orbits of nearby planetesimals, flinging some outward toward the edges of the solar system, dragging others inward toward the Sun, and trapping many in a broad band of disturbed orbits between Mars and Jupiter, a region we now call the asteroid belt. The asteroid belt is often depicted in movies as a dense, dangerous field of tumbling boulders, where spacecraft must dodge and weave to survive. The reality is the opposite. The belt is almost entirely empty. If you stood on any single asteroid and looked around, the nearest neighbor would typically be millions of kilometers away, so far that it would be invisible to the naked eye. The total mass of the entire asteroid belt, every rock, every grain, every pebble, adds up to less than 4% of the mass of our moon. It is a vast, sparse graveyard of planetary building material that never became a planet, disrupted and scattered by Jupiter before it had the chance. But among those failed worlds, the most scientifically precious are the small, dark, carbon-rich bodies, the C-types, billions of small bodies, rocks, boulders, loose aggregates of dust and ice, were scattered across the solar system by the gravitational bullying of Jupiter and the other giant planets. They were flung into orbits that kept them too far apart to merge, too small to grow, too insignificant to matter. They became asteroids, and for 4.5 billion years, they have been drifting in the dark, unchanged, unaltered, carrying inside them the original chemistry of the solar system's birth. Think about that for a moment. When you hold a piece of an asteroid in your hand, you are not holding a rock from some distant world. You are holding a piece of the raw material that everything was made from. The Earth was made from this stuff. The Moon, Mars, you. Every atom in your bones passed through a cloud like this. But the atoms in your body have been recycled, melted, compressed, erupted, dissolved, consumed, and rebuilt across billions of years of planetary evolution. The atoms in an asteroid have not. They are still in their original arrangement. They are the universe's baby photos, frozen in time. And that is why scientists want them so badly. The idea of sending a spacecraft to collect a sample from an asteroid did not appear overnight. It was born from decades of frustration. For most of the 20th century, the only way to study asteroids was to look at them through telescopes. You could measure their brightness. You could estimate their size. You could track their orbits with extraordinary precision. But you could not touch them. You could not smell them, taste them, weigh their grains under a microscope, or run them through a mass spectrometer. You were stuck looking through a window at a house you could never enter. Meteorites offered a partial solution. Every year, thousands of space rocks fall to Earth, and some of them are fragments of asteroids. Scientists have been collecting and analyzing meteorites for centuries. A class of meteorites called carbonaceous chondrites, named for their high carbon content and the tiny round mineral grains, called chondrules, embedded within them, were known to contain organic molecules, water-bearing minerals, and even amino acids. In 1969, a meteorite called Murchison fell in rural Australia, and when chemists analysed it, they found over 70 different amino acids, many of which do not exist naturally on Earth. It was a landmark discovery. It proved that complex organic chemistry was happening in space, independently of biology. But meteorites have a problem. They have been contaminated. The moment a meteorite enters Earth's atmosphere, it is bathed in superheated plasma. When it hits the ground, it is exposed to water, bacteria, oxygen, and human hands. By the time it reaches a laboratory, it has been altered. Every measurement carries an asterisk. Every amino acid could be terrestrial contamination. Every water molecule might have come from rain, not from space. For scientists trying to understand the pristine chemistry of the early solar system, meteorites were tantalizing but unreliable witnesses. The solution was obvious but terrifying. Go to the asteroid. Collect a sample in the vacuum of space, where no atmosphere, no water, and no biology could contaminate it. Seal it, bring it home, and study it in the cleanest laboratories on Earth. Easier said than done. The distances involved are staggering. Ryugu, at its closest approach to Earth, is still roughly 300,000 kilometers away, but that is misleading because a spacecraft does not fly in a straight line. The actual trajectory of a mission to Ryugu involves looping around the Sun, using Earth's gravity as a slingshot, and matching the asteroid's orbital speed and direction with surgical precision. The total distance traveled by the spacecraft that visited Ryugu was more than 5 billion kilometers. If you could drive that distance in a car at highway speed, it would take you roughly 6 million years. And when you arrive, the asteroid is not sitting still waiting for you. Ryugu rotates once every 7.6 hours. Its surface is covered in boulders. Some of them are the size of houses. There are no flat landing pads, no smooth plains, no safe harbors. The gravity is so weak, roughly 60,000 times weaker than Earth's, that a spacecraft cannot land in the traditional sense. It would bounce off and drift away. Collecting a sample requires a mechanism so precise and so gentle that it can touch the surface for less than a second, fire a projectile into the rock to kick up debris, capture that debris in a sealed container, and then ascend back to orbit, all without tipping over, without bouncing, without losing the sample, and without crashing into a boulder. This is the mission that Japan decided to build. The Japan Aerospace Exploration Agency, known by its acronym JAXA, had already attempted something like this once before. In 2003, they launched a spacecraft called Hayabusa, the Japanese word for peregrine falcon, toward a small asteroid called Itokawa. The mission was plagued with problems. 2 of its 4 ion engines failed. Its reaction wheels, the spinning devices that control orientation, broke down. Its small lander, named Minerva, missed the asteroid entirely and drifted off into space. When Hayabusa finally attempted to collect a sample, the collection mechanism malfunctioned. The spacecraft touched the surface, but did not fire its sampling projectile. It bounced, it tumbled, it lost communication with Earth for weeks. At one point, mission controllers believed the spacecraft was dead, and yet somehow Hayabusa limped home. In June of 2010, its sample return capsule streaked across the sky above the Australian outback like a man-made shooting star and landed in the Woomera test range. When scientists opened it, they found a few hundred microscopic grains of dust from asteroid Itokawa, so small they could barely be seen with the naked eye. It was the first time in human history that material had been deliberately collected from the surface of an asteroid and returned to Earth. The mission was a triumph of stubbornness, but JAXA knew they could do better. The lessons from Hayabusa 1 were brutal and comprehensive. The reaction wheel failures meant the spacecraft could not point itself accurately. The ion engine failures meant the trajectory had to be recalculated on the fly. The failed lander deployment meant the surface characterization data that would have informed the sample collection attempt was never obtained. And the sampling mechanism failure, the most painful of all, meant that the microscopic grains found inside the capsule were likely surface particles kicked up by the spacecraft's own contact with the surface, not material deliberately excavated by the sampling projectile. The mission had succeeded in returning something, but it had not succeeded in the way it was designed to. JAXA's engineers dissected every failure with the meticulous honesty that defines the best of Japanese engineering culture. Each malfunction was traced to its root cause. Each root cause was addressed with a redesign, a redundancy, or a procedural change. The new spacecraft would have improved reaction wheels with better bearings and longer operational lifetimes. It would have redesigned ion engines with higher reliability. Its sampling mechanism would be tested more rigorously. Its navigation systems would be upgraded to handle autonomous descent in environments far more challenging than Itokawa's relatively benign surface. They spent the next several years designing Hayabusa's successor. They called it Hayabusa 2, and this time they chose a very different target. Itokawa had been an S-type asteroid, a rocky, stony body made mostly of silicate minerals. Scientifically interesting, but not the jackpot. The real prizes were the C-type asteroids, the carbonaceous ones. These are the dark, carbon-rich bodies thought to be the most primitive objects in the solar system. They are the ones most likely to contain water, organic molecules, and the kind of unaltered pre-solar material that could tell us what the solar system looked like before the planets formed. And among the C-type asteroids accessible to a spacecraft launched from Earth, one stood out, a small dark body designated 1993 JU3. Later, it would be given a name, Ryugu. The selection of Ryugu was not romantic, it was mathematical. JAXA needed an asteroid that met a brutal set of criteria. It had to be close enough to reach with the available fuel. Its orbit had to be well known enough to calculate a precise rendezvous trajectory. Its size had to be large enough to study, but small enough that its gravity would not complicate sample collection. Its spectral signature, the way it reflected light at different wavelengths, had to confirm it was a C-type body rich in carbon and potentially in water-bearing minerals. Ryugu checked every box. The decision to target a C-type asteroid was driven by something deeper than curiosity. It was driven by urgency. By the early 2000s, the question of life's origins had become one of the most contested problems in science. The old model that life arose spontaneously on Earth from a soup of simple chemicals energized by lightning, the famous Miller-Urey experiment from 1953, was crumbling under the weight of new evidence. The experiment had shown that amino acids could be synthesized from methane, ammonia, water vapor, and hydrogen under electrical discharge. But the atmosphere of the early Earth was almost certainly not rich in methane and ammonia. It was more likely dominated by carbon dioxide and nitrogen, a mixture far less conducive to organic chemistry. The warm little pond that Charles Darwin had imagined, the cozy cradle where life spontaneously assembled itself, was looking less and less plausible. At the same time, the discovery of extremophile organisms on Earth, bacteria thriving in boiling hot springs, freezing Antarctic ice, and the crushing depths of the ocean floor, had expanded the definition of habitable environments so dramatically that scientists were forced to reconsider where life could begin. If life could survive in those conditions, perhaps it could originate in equally extreme places. Perhaps the origin of life was not a gentle event in a sheltered lagoon, but a violent process at the interface of rock and water deep beneath the Earth's surface. Or perhaps, and this was the most radical idea of all, the origin of life did not happen on Earth at all. Perhaps the first organic molecules, the first amino acids, the first self-replicating chemistry arose in space and was delivered to Earth by asteroids and comets during the late heavy bombardment. This idea, called panspermia in its strongest form, or exogenous delivery in its more conservative version, was not new. It had been proposed in various forms since the 19th century. But it had always been speculative. There was no direct evidence that space-borne organic molecules could survive the fiery violence of atmospheric entry and the shattering impact of landing. There was no proof that asteroid-delivered amino acids were chemically compatible with the biochemistry of life on Earth, and there was no way to distinguish between amino acids that had arrived from space and amino acids that had formed on Earth, since both would be made of the same elements, the same bonds, the same molecular structures. Ryugu was supposed to help settle this debate. A pristine sample, untouched by Earth's environment, would provide an unambiguous baseline. Whatever amino acids and organic molecules were found in Ryugu's dust could not be contamination. They were real, they were extraterrestrial, and their abundance, their chirality, the handedness of their molecular structure, and their isotopic composition could be compared directly with terrestrial biology to test whether a connection existed. The stakes could not have been higher. And when Hayabusa 2 launched on that December morning in 2014, trailing a plume of exhaust into the bright sky above Tanegashima, it carried with it the weight of one of the oldest questions in human thought. Where do we come from? On December 3, 2014, Hayabusa 2 launched from the Tanegashima Space Center on a small island off the southern tip of Japan. It rode an HIA rocket into orbit, deployed its solar panels, and began a journey that would take 3.5 years. To reach Ryugu, the spacecraft performed an Earth gravity assist, swinging past our planet in December of 2015 to steal a tiny amount of orbital energy, and then spent the next 2.5 years coasting through interplanetary space, its 4 ion engines firing intermittently, nudging it along a trajectory so carefully calculated that the margin of error was measured in meters per second. On June 27, 2018, Hayabusa 2 arrived at Ryugu, and what it saw stunned everyone. The asteroid was shaped like a diamond, or, more precisely, like a spinning top. A nearly perfect geometric shape with a prominent equatorial ridge, a flattened top, and a flattened bottom. This was not what the models had predicted. Computer simulations had suggested a more irregular potato-like shape. Instead, Ryugu looked almost designed. Its equatorial ridge was sharp, pronounced, and continuous, as if someone had taken a sphere of rubble and spun it until centrifugal force squeezed it into a rhombus, which, as it turned out, is almost exactly what had happened. Ryugu's shape was the result of a faster spin rate earlier in its history, a period when the asteroid rotated so quickly that loose material migrated toward the equator and piled up into a ridge. The asteroid was literally shaped by its own rotation, but the real shock was the surface. Scientists had hoped to find at least a few smooth areas, patches of fine-grained regolith, the powdery soil that accumulates on airless bodies over time. Instead, Ryugu was covered in boulders. Everywhere, hundreds of them, thousands. Some were the size of cars, some were the size of office buildings. The largest single boulder on Ryugu, nicknamed Otohime, was nearly 150 meters across, taller than the Leaning Tower of Pisa. There was almost nowhere flat enough to safely touch down. The mission, that had been designed around a relatively smooth surface, was now facing a landscape that looked like a construction site after an earthquake. And that was when the engineers realized their real challenge was only beginning. But to appreciate the depth of that challenge, you need to understand something about the kind of object Ryugu is, and why that kind of object matters more than almost anything else in planetary science. Asteroids are not all the same. They come in classes, defined primarily by their composition and their reflectivity. The most common type, making up roughly 75% of all known asteroids, is the C-type, the carbonaceous asteroids. These are the dark ones, the ancient ones. They reflect so little light that early astronomers often missed them entirely, their dim surfaces blending into the blackness behind them. For decades, C-type asteroids were considered the least interesting members of the solar system's small body population. They were too faint to study in detail, too far away to visit cheaply, too fragile. Many of them appeared to be loosely bound rubble piles rather than solid rocks, to be considered viable targets for exploration. That perception changed in the 1990s when laboratory analysis of carbonaceous chondrite meteorites, the rocks thought to originate from C-type asteroids, began to reveal a chemical complexity that no one had expected. These meteorites did not just contain carbon. They contained organic molecules, compounds of carbon bonded with hydrogen, oxygen, nitrogen, and sulfur, in arrangements that, on Earth, are associated almost exclusively with biological processes. Amino acids, nuclear bases, sugar-related molecules, fatty acids that could form the membranes of primitive cells. The meteorites were not alive, but they contained the chemical vocabulary of life, written in stone that had formed before any planet existed. The implications were profound. If these molecules formed naturally in the cold, radiation-bathed environment of the early solar system, without biology, without liquid water, without any of the conditions we associate with life on Earth, then the raw ingredients of biology were not a product of planetary evolution. They were a precondition of it. They existed before the planets. They were delivered to the young Earth by the same rocks that helped build it. Every amino acid in your body might trace its ultimate ancestry, not to some warm pond on ancient Earth, but to a frozen grain of dust in the pre-solar nebula 4.5 billion years ago. But this was still a hypothesis. The meteorite evidence was suggestive, not conclusive. Those meteorites had fallen through Earth's atmosphere, landed in fields and deserts, and been handled, sometimes for years, before reaching a laboratory. Contamination was always a possibility, always a caveat, always an asterisk next to every result. To remove that asterisk, scientists needed a sample that had never touched Earth's air, Earth's water, or Earth's biology. A sample collected in the vacuum of space and delivered directly to a sterile laboratory. That is what Hayabusa 2 was designed to do. The spacecraft itself was a masterpiece of Japanese engineering, compact, efficient, and bristling with instruments. It weighed roughly 600 kilograms at launch, about the mass of a large horse. Its body was a rectangular box roughly 1 meter on each side, covered in solar cells that generated about 2.6 kilowatts of power at Earth's distance from the Sun, enough to run a few household appliances. It carried 4 ion engines, each producing a thrust of about 10 millinewtons, a force so small that if you held the engine in your hand, you would barely feel it. But in the frictionless vacuum of space, that tiny push, sustained over months and years, could accelerate the spacecraft to speeds of tens of thousands of kilometers per hour. The ion engines used xenon gas as propellant. Xenon atoms were ionized, stripped of their electrons, and then accelerated through an electric field, shooting out the back of the engine at speeds of roughly 30 kilometers per second. The efficiency was extraordinary. Hayabusa 2 carried only about 66 kilograms of xenon, yet that small supply was enough to provide all the velocity changes needed for the 3.5-year outbound journey, the 16 months of asteroid operations, and the year-long return trip to Earth. A conventional chemical rocket would have needed vastly more fuel, making the mission either impossible or prohibitively expensive. But the spacecraft's most critical component was its sampling mechanism, the device at the heart of the entire mission. It was called the sampler horn, and it was elegantly simple. A conical tube, roughly 1 meter long, extending from the bottom of the spacecraft. When the horn touched the asteroid's surface, a small tantalum projectile, a metal slug about the size of a marble, weighing roughly 5 grams, would be fired downward at a speed of roughly 300 meters per second. The impact would shatter the surface material and launch fragments upward into the horn, where a funnel-shaped catcher would guide them into one of 3 sealed sample containers, lettered A, B, and C. Each container could hold a few grams of material. The system was designed to operate in near-zero gravity, on a surface that might be anything from solid basalt to loose sand to a treacherous maze of jagged rubble. There was no second chance built into the design. If the sampler failed, there was no backup. The mission would return empty-handed. Hayabusa 2 also carried a small fleet of deployable surface explorers, the most ambitious suite of surface probes ever sent to a small body. 2 small rovers, collectively called Minerva 2-1, each about the size of a large tin can and weighing roughly 1 kilogram, were designed to hop across the surface using an internal rotating mass. In Ryugu's negligible gravity, a small torque from the spinning mass would launch the rover into a gentle arc covering meters with each hop, a mode of locomotion that would be absurd on Earth but was perfectly suited to a world where jumping was the only practical way to move. A third rover, Minerva 2-2, was held in reserve, and a small lander called Mascot, the mobile asteroid surface scout, built by the German and French space agencies, carried its own instruments, including a thermal radiometer, a magnetometer, a camera, and an infrared spectrometer. Mascot had a single hop available to it, powered by a swing arm, and a battery life of roughly 16 hours. The deployment of these surface probes was itself a landmark. On September 21, 2018, Minerva 2-1, consisting of rovers designated 1A and 1B, was released from an altitude of about 55 meters above Ryugu's surface. The tiny robots tumbled downward in the feeble gravity, bouncing gently on contact, and began hopping. They sent back the first images ever taken from the surface of an asteroid. The photographs were surreal, close-up views of a landscape of dark, angular boulders under a pitch-black sky, with the sun a brilliant point of light casting razor-sharp shadows across a surface that looked like a demolished parking lot. Some images were motion-blurred, captured mid-hop, the horizon tilting wildly as the rover tumbled through its low-gravity arc. On October 3, 2018, Mascot was deployed. It descended for about 6 minutes, bouncing once on landing, and then began its 16-hour mission. Its instruments measured surface temperatures, mineral compositions, and magnetic field strength. Mascot confirmed what the orbital instruments had suggested. Ryugu's surface was extremely dark, extremely porous, and composed of material consistent with heated carbonaceous chondrite. But it added a crucial new detail. The rocks were not uniform. They showed 2 distinct textures, some rough, some smooth, suggesting that Ryugu's parent body, the larger asteroid from which Ryugu was born, had experienced uneven heating or aqueous alteration at some point in its ancient past. After 16 hours, Mascot's battery died, and the little lander fell silent on the surface of Ryugu, never to be heard from again. Its data, however, would prove invaluable in the months and years that followed. With the surface probes deployed and the orbital survey well underway, the mission turned its full attention to the task that justified everything: the sample collection. And that is where the real drama began. The first high-resolution images of Ryugu's surface arrived at JAXA's mission control in Sagamihara, Japan, in early July of 2018. Engineers and scientists gathered around monitors, expecting to confirm what the orbital models had suggested: a surface with at least some broad, flat regions where the spacecraft could safely descend for sample collection. What they saw instead was a nightmare. Every candidate landing site was strewn with boulders, not scattered boulders with generous gaps between them. Dense fields of rock, some interlocking, some perched precariously atop one another, all casting sharp shadows across a surface so dark it was difficult to distinguish individual features. The original mission plan had assumed the spacecraft could target a landing ellipse, roughly 50 meters in diameter, a circle about the size of half a football field, On a smooth surface, that would have been generous. On Ryugu, it was suicide. There was not a single 50-meter patch anywhere on the visible surface that did not contain at least one boulder large enough to destroy the spacecraft on contact. The mission planners had a problem. Hayabusa 2 had traveled more than 3 billion kilometers to reach this asteroid. It was carrying the most sophisticated sample collection mechanism ever built for deep space. It had a suite of cameras, spectrometers, and thermal sensors designed to characterize the surface in unprecedented detail, and it could not land. But here is the problem. Hayabusa 2 was not designed to hover indefinitely. Its fuel was finite. Its mission timeline was locked to orbital mechanics. The spacecraft had to depart Ryugu by November of 2019 to make its return trajectory to Earth. Every day spent solving the landing problem was a day not spent doing science. And the entire point of the mission, the entire reason Japan had spent approximately 15 billion yen, the entire reason hundreds of engineers had spent a decade of their careers building this spacecraft, was to bring home a sample. Without a successful touchdown, the mission would be remembered as a spectacular flyby, impressive but incomplete. The engineers did something remarkable. They rewrote the mission. The original plan had called for the spacecraft to descend autonomously, using its onboard navigation system to identify a safe landing zone in real time. But the boulders made autonomous navigation too risky. The computer could not reliably distinguish between safe ground and a boulder's shadow. So the team developed a new approach. They would place a target marker, a small reflective ball about the size of a baseball, covered in retroreflective material, onto the surface first. The marker would serve as a beacon. When the spacecraft descended for its sample collection run, it would track the marker with its cameras and use it as a reference point to guide itself down with centimeter-level precision. But placing the marker required its own descent, a practice run, almost as dangerous as the real thing. And finding a spot to place it required identifying the least deadly patch of ground on the entire asteroid. The team spent weeks analyzing images, building three-dimensional terrain models, measuring boulder heights and shadow angles, calculating the spacecraft's footprint during descent. They identified a candidate site in Ryugu's southern hemisphere, designated L08. It was not flat, it was not smooth, but it had a gap between boulders just barely wide enough, roughly 6 meters across, for the spacecraft's sampling horn to reach the surface without striking a rock. 6 meters. The spacecraft itself was roughly 6 meters from tip to tip across its solar panels. They were threading a needle at a distance of 300 million kilometers from home, with a signal delay of roughly 16 minutes each way. By the time Mission Control saw what the spacecraft was doing, whatever it was doing had already happened 16 minutes ago. There was no joystick, no manual control. The spacecraft had to do this alone. On October 25, 2018, Hayabusa 2 performed its first practice descent. It dropped a target marker toward the surface and watched it bounce. In Ryugu's feeble gravity, the ball bounced for nearly 10 minutes before finally settling. The marker landed within the target zone. The team exhaled, but the real test was still ahead. Meanwhile, the spacecraft's instruments were revealing something deeply puzzling about Ryugu's composition. The near-infrared spectrometer aboard Hayabusa 2 detected a clear absorption feature at a wavelength of 2.72 micrometers, a signature associated with hydroxyl groups, which are components of water-bearing minerals called phyllosilicates. Ryugu contained hydrated minerals. Water, or at least the chemical remnants of water, was locked inside the rock. This was expected for a C-type asteroid, but the strength of the signal was weaker than anticipated. The asteroid was drier than its spectral classification had suggested. And it gets worse. The thermal data was strange too. Ryugu's surface temperature swung wildly between day and night, far more than it should have if the surface were made of solid rock. Solid rock stores heat. It warms up slowly and cools down slowly, the way a stone wall stays warm long after the sun sets. But Ryugu's surface was behaving like gravel. It heated up fast and cooled down fast, suggesting that the surface material was porous, loosely packed, and full of gaps. The asteroid was not a solid body with a rubble coating. It was rubble all the way through, a pile of debris held together by nothing more than the faintest gravitational attraction between its constituent pieces, so faint that a strong human sneeze, if somehow delivered in a vacuum, could theoretically launch a pebble off the surface and into orbit. This raised a terrifying question for the sample collection team. If the surface was this fragile, if it was essentially a loose pile of gravel with no cohesion, what would happen when the spacecraft fired its sampling projectile? The plan called for Hayabusa 2 to descend until its meter-long sampling horn, a tapered tube extending from the bottom of the spacecraft, touched the surface. At the moment of contact, a small tantalum bullet would be fired downward at 300 meters per second, blasting surface material upward into the horn, where it would be funneled into a sealed collection chamber. The entire touchdown was designed to last less than 1 second. But on a surface this fragile, the bullet might not just kick up dust. It might destabilize the entire landing area. The spacecraft could sink. It could trigger a local collapse. It could be buried. Nobody knew. No spacecraft had ever attempted to collect a sample from a body this small, this dark, or this structurally weak. Every simulation was a guess. Every model contained assumptions that had never been tested against reality, and the only way to find out was to try. On February 22nd, 2019, nearly 8 months after arriving at Ryugu, Hayabusa 2 began its first touchdown descent. The spacecraft started from its home position, a station keeping point roughly 20 kilometers above the surface, and began a slow, controlled fall toward the asteroid. Over the next several hours, it dropped lower and lower, its cameras tracking the target marker on the surface, its altimeter measuring the shrinking distance, its attitude thrusters firing in precise bursts to maintain alignment. At an altitude of about 45 meters, the spacecraft switched to fine guidance mode. The target marker's reflected flash, illuminated by the spacecraft's own flash lamp, became the primary navigation reference. The descent rate slowed to centimeters per second. The boulders below grew from specks to monsters in the camera feed. In mission control, the room was silent. 16 minutes away by light, the spacecraft was on its own. At 5 minutes past 7 in the morning, Japan Standard Time, the sampling horn made contact with the surface. The spacecraft detected the touch and immediately fired the tantalum projectile. A plume of dark debris erupted from the surface. Later analysis of the camera footage revealed a cone-shaped cloud of shattered rock and dust expanding outward at roughly 2 meters per second. The spacecraft's thrusters fired, and Hayabusa 2 leaped back upward, ascending rapidly away from the chaos below. The entire surface contact lasted less than 1 second. The footage, when it was transmitted back to Earth, was extraordinary. Frame by frame, you could see the moment of impact. The horn pressing into the dark gravel, the flash of the projectile firing, the eruption of debris, and then the rapid ascent. Fragments of Ryugu hung in the near-zero gravity like a slow-motion explosion, drifting lazily in all directions, some pieces tumbling, end over end, catching glints of sunlight as they spun. It looked like a controlled demolition performed on a world with no weight. The sample chamber telemetry confirmed that material had entered the horn. The team would not know exactly how much until the capsule returned to Earth, but the signs were promising. The first touchdown was a success, but JAXA was not done. The mission plan included a far more audacious objective, one that had never been attempted anywhere in the history of space exploration. They were going to create an artificial crater on Ryugu's surface, exposing subsurface material that had been shielded from space weathering and solar radiation for potentially billions of years. And then they were going to land again, inside or near that crater, and collect a second sample from beneath the surface. The device was called the Small Carry-On Impactor, or SCI. It was, in essence, a bomb, a 2-kilogram copper plate backed by 4.5 kilograms of plastic explosive. The plan was to separate the SCI from the spacecraft, retreat to a safe distance behind the asteroid, and then detonate the explosive remotely. The explosion would accelerate the copper plate to roughly 2 kilometers per second, fast enough to blast a crater into the surface several meters wide. The risks were significant. The detonation would occur just 300 meters above Ryugu's surface. Debris from the impact would be launched in all directions, and in Ryugu's negligible gravity, Some of that debris could reach altitudes of hundreds of meters, potentially high enough to strike the retreating spacecraft. To survive, Hayabusa 2 had to execute a precise evasive maneuver, ducking behind the far side of the asteroid before the copper plate struck the surface. The timing had to be exact. Too slow, and the spacecraft would be in the line of fire. Too fast, and it would miss the observation window needed to confirm the crater's creation. On April 5, 2019, the SCI was deployed. Hayabusa 2 released the impactor, fired its thrusters, and began a rapid retreat to the far side of Ryugu. A small deployable camera, DCAM-3, was released separately to observe the impact from a safe vantage point. 40 minutes after separation, the explosive detonated. The copper plate struck the surface. DCAM-3 captured the moment. A curtain of dark ejecta, shattered rock and dust, erupted from the surface in a hemispherical sheet, expanding outward and upward like a fountain filmed in extreme slow motion. The plume rose to an estimated height of several hundred meters, its edges sharp against the blackness of space, individual fragments catching sunlight as they sailed upward on ballistic trajectories that, in normal gravity, would have brought them back to Earth in seconds, but in Ryugu's gravity would take hours. When the debris had cleared, and Hayabusa 2 cautiously returned to observe the impact site, the crater was clearly visible. It was roughly 14.5 meters in diameter and about 2 to 3 meters deep, far larger than pre-impact simulations had predicted. The surface had yielded more easily than expected. The rubble pile structure, which had been inferred from thermal data, was now confirmed by direct experiment. Ryugu was soft. Its surface had almost no strength. The crater's rim was sharp and well-defined, and the exposed subsurface material appeared slightly different in color, redder, less weathered than the surrounding terrain. The team now had to land again, this time near the crater. But here is what makes this truly terrifying. The crater had changed the local terrain in ways that could not be fully characterized from orbit. New boulders had been displaced. Fine debris had been redistributed. The topography around the impact site was different from anything the team had mapped before the explosion. Landing near a fresh crater on a rubble pile asteroid, 300 million kilometers from Earth, with no possibility of real-time control, was not just risky. It was the kind of risk that mission planners spend their careers avoiding. And yet, on July 11, 2019, Hayabusa 2 descended again. This time, the target was a site designated C01, located about 20 meters north of the artificial crater. The descent profile was similar to the first touchdown, slow, controlled, camera-guided, but the stakes felt higher. This was bonus material. The mission's primary objective had already been achieved. A failure here would not erase the first touchdown's success, but it would be a public disaster. And more importantly, the subsurface material accessible near the crater was scientifically irreplaceable. It might contain molecules that had been shielded from cosmic radiation for the entire age of the solar system. Molecules untouched since before the Earth existed. The second touchdown occurred at 9:36 in the morning, Japan Standard Time. The sampling horn touched the surface, the projectile fired, debris erupted, and the spacecraft ascended. The operation lasted less than 1 second. Telemetry confirmed that material had entered the collection chamber. For the second time, Hayabusa 2 had kissed an asteroid and stolen a piece of it. The contrast between the two samples, one from the weathered surface, one from near the pristine subsurface exposed by the crater, would prove to be one of the most scientifically valuable aspects of the entire mission. No previous sample return mission had collected material from two distinct locations on the same body, let alone from two locations with such different exposure histories. The surface sample represented material that had been battered by solar wind, cosmic rays, and micrometeorite impacts for millions of years. The subsurface sample represented material that had been shielded from all of that, protected beneath a blanket of rubble, sealed away in conditions that had barely changed since the parent body was shattered, and Ryugu was assembled from its wreckage. Having both samples from the same asteroid allowed scientists to do something unprecedented. They could measure exactly what space weathering does to the chemistry of a C-type asteroid. not by comparing different bodies with different compositions and different histories, but by comparing two portions of the same body with different exposure histories. The surface sample was the control, the subsurface sample was the experiment, and the differences between them revealed, for the first time, the precise chemical cost of living in space, the molecular toll that billions of years of radiation and bombardment exact on the most delicate organic molecules. But the real magnitude of what had just been accomplished would not become clear for another 18 months, because the samples were sealed inside a return capsule, inside a spacecraft, still orbiting an asteroid 300 million kilometers from Earth. Getting them home would require a journey nearly as harrowing as the one that had brought Hayabusa 2 to Ryugu in the first place. And when those samples finally arrived, when the capsule screamed through Earth's atmosphere at 12 kilometers per second and parachuted into the Australian desert in December of 2020, what the scientists found inside would force them to rewrite fundamental assumptions about the chemistry of the early solar system. Something was wrong with the story we had been telling ourselves about where life's ingredients came from, and the 5.4 grams of black dust sitting in a sealed container in Sagamihara, Japan, was about to prove it. To understand why those 5.4 grams were so dangerous to existing theories, you need to understand what scientists expected to find, and how thoroughly Ryugu's dust shattered those expectations. The prevailing model of amino acid formation in the early solar system, refined over decades of meteorite analysis and laboratory simulations, went roughly like this. In the cold outer regions of the pre-solar nebula, far from the young sun, where temperatures hovered near negative 260 degrees Celsius, simple molecules like water, ammonia, methanol, and carbon monoxide froze onto the surfaces of tiny dust grains, forming thin, icy mantles. Ultraviolet radiation from nearby stars penetrated the nebula and bombarded these icy coatings, breaking and reforming chemical bonds, driving reactions that produced increasingly complex organic molecules. Over millions of years, this radiation-driven chemistry, called photolysis, built up a library of organic compounds on the surfaces of those grains, including amino acids and their precursors. When the nebula collapsed and the solar system began to form, those grains were incorporated into the planetesimals that eventually became asteroids. If an asteroid was large enough and contained enough radioactive material, particularly the isotope aluminum-26, which was abundant in the early solar system and decayed rapidly, releasing heat, its interior would warm up. Water ice would melt, liquid water would percolate through the rock, dissolving minerals, altering crystal structures, and creating the conditions for aqueous chemistry, chemical reactions in a water solution. This aqueous alteration was thought to be the key step. It was the warm bath that took the raw organic ingredients, created by ultraviolet radiation, and refined them, rearranging bonds, selecting for certain molecular configurations, concentrating amino acids into forms that were biologically relevant. The model was elegant, it was testable, it was supported by decades of meteorite data, and it made a clear prediction. Asteroids that had experienced more aqueous alteration, more heating, more contact with liquid water, should contain more amino acids. The chemical richness of life's building blocks should correlate with the degree to which the rock had been cooked and soaked. Ryugu's samples did not follow this prediction. When the initial chemical analyses were published, beginning in 2022, the results were bewildering. Ryugu's dust contained amino acids. 23 different types were identified in the first comprehensive analysis, including glycine, alanine, and several others found in terrestrial proteins. But the concentrations were lower than expected. Much lower, carbonaceous chondrite meteorites, like Murchison, which showed extensive evidence of aqueous alteration, contained amino acid concentrations roughly 10 to 100 times higher than what was measured in Ryugu's material. This was confusing. Ryugu was supposed to be the pristine version of Murchison, the uncontaminated original. If the amino acids in meteorites were real and not terrestrial contamination, then Ryugu should have contained similar or even higher concentrations, since its samples had never been exposed to Earth's environment. Instead, the concentrations were lower. Either the meteorites had been contaminated, and the decades of amino acid research based on them was built on a false foundation, or something about Ryugu's specific history had suppressed amino acid formation. The answer, when it emerged, was both simpler and more unsettling than either possibility. Ryugu had been heated, not by radioactive decay alone, but by the sun. Orbital calculations showed that Ryugu's orbit had brought it much closer to the sun in the geologically recent past, perhaps within the last few million years. During those close approaches, the asteroid's surface temperature had risen high enough to partially degrade some of the more fragile organic molecules. The amino acids were still there, but they had been damaged. Some had been broken down into simpler fragments. Others had been altered by the thermal stress. This meant that the amino acids found in Ryugu were survivors. They were the molecules tough enough to endure millions of years of intermittent solar heating on the surface of a body with no atmosphere, no magnetic field, and no protection from the full fury of ultraviolet radiation and charged particles streaming outward from the sun. The more delicate molecules, the ones that might have been most scientifically interesting, were gone, destroyed by the very star that had given the solar system life. But the second touchdown sample, the one collected near the artificial crater, told a different story. That material had been shielded from the sun. It had been buried beneath the surface, protected by meters of overlying rubble for potentially billions of years. And when scientists analyzed it, they found organic molecules in greater abundance and greater variety than the surface sample. The subsurface material was richer, less degraded, closer to the primordial state. This confirmed something that planetary scientists had long suspected but had never been able to prove with direct evidence. The surfaces of asteroids are not representative of their interiors. Space weathering, the cumulative effect of solar radiation, cosmic rays, and micrometeorite impacts, alters the surface chemistry of airless bodies over time, breaking down complex molecules, changing mineral structures, and darkening surfaces. The real chemistry of an asteroid lives beneath its skin, and getting to it requires either drilling, which is mechanically challenging in microgravity, or doing what Hayabusa 2 did, blasting a hole and reaching in. The amino acid discoveries were dramatic, but they were not the most important finding in Ryugu's dust. That distinction belongs to something far more subtle and far more consequential: the water. Not liquid water, not ice. Water locked inside the crystal structure of minerals. Hydroxyl groups bonded to magnesium and iron in a class of minerals called phyllosilicates. These are the same minerals found in terrestrial clay, the stuff that makes mud sticky. On Earth, phyllosilicates form when rock reacts with liquid water over extended periods. Their presence in Ryugu confirmed that Ryugu's parent body, the larger asteroid that was destroyed to create Ryugu, had once contained liquid water, actual flowing, dissolving, chemically active liquid water, circulating through the rock like groundwater through limestone. The isotopic composition of that water was the bombshell. Water molecules come in different isotopic flavors, depending on whether their hydrogen atoms are ordinary hydrogen or deuterium, a heavier variant with an extra neutron in its nucleus. The ratio of deuterium to hydrogen, called the D/H ratio, is a fingerprint. Different water sources in the solar system have different D/H ratios. Earth's ocean water has a specific ratio. Cometary water tends to have a much higher ratio, roughly 2 to 3 times higher than Earth's oceans. The water in Ryugu's minerals had a D/H ratio that was remarkably close to Earth's ocean water. Let that sink in. The water locked inside this 4.5 billion-year-old space rock, orbiting between Earth and Mars, had the same isotopic fingerprint as the water in your glass, in your blood, in every ocean on this planet. This was powerful evidence for a hypothesis that had been debated for decades, that a significant fraction of Earth's water was delivered by asteroids during the late heavy bombardment, a period roughly 3.8 to 4.1 billion years ago, when the inner solar system was pummeled by a storm of small bodies dislodged from the outer reaches by the gravitational upheaval of the giant planets. If that hypothesis is correct, then the water you drink is not from Earth, it is from space, delivered by rocks like Ryugu billions of years ago, accumulated drop by microscopic drop across millions of impacts, until the young Earth's surface was covered in oceans that it never made for itself. And it was in those oceans of alien water, that life began. The scientific community was electrified. Ryugu was not just an asteroid, it was a Rosetta Stone, a key to deciphering the origin of the most important substance on our planet. But the findings also raised questions that nobody had anticipated. Questions that, in some cases, threatened to overturn decades of settled science. One of the most provocative findings concerned pre-solar grains, tiny particles embedded within Ryugu's matrix that were older than the solar system itself. These grains, some made of silicon carbide, others of diamond just nanometers across, formed in the atmospheres of dying stars, red giants, supernovae, asymptotic giant branch stars, and were ejected into the interstellar medium long before our solar nebula condensed. They drifted through the galaxy for millions or even billions of years before being incorporated into the cloud of gas and dust that would become our solar system. They are, in a very literal sense, stardust, and Ryugu's samples contained them. The isotopic ratios in these pre-solar grains were wildly different from anything found in the solar system. Their carbon, nitrogen, and oxygen isotopes bore the signatures of nuclear processes that occurred in stars with masses and compositions very different from our Sun. Each grain was a message in a bottle from a dead star, a record of nucleosynthesis in a stellar furnace that burned out billions of years before Earth existed. And the fact that these grains survived intact inside Ryugu, unmelted, unaltered, still carrying the isotopic fingerprints of their parent stars, told scientists something crucial about Ryugu's thermal history. The parent body of this asteroid was never heated to temperatures high enough to destroy pre-solar grains. It was gently warmed, enough for liquid water to flow and minerals to alter, but not enough to erase the most ancient records embedded in its fabric. This placed strict constraints on the size and composition of Ryugu's parent body. Too large, and radiogenic heating from aluminum-26 would have cooked the interior beyond the survival threshold of pre-solar grains. Too small, and there would not have been enough internal heat to drive aqueous alteration at all. The parent body had to be in a narrow sweet spot, probably between 50 and 100 kilometers in diameter, large enough to warm its core but not large enough to melt it. And here was another puzzle. Ryugu itself is only about 870 meters across, a mote of dust compared to its parent. Somewhere in the asteroid belt, billions of years ago, a body 50 to 100 kilometers wide, a body large enough to be considered a minor planet, was shattered by a catastrophic collision. The fragments reassembled under their own gravity into a new, much smaller object, a rubble pile. That rubble pile eventually migrated inward from the main asteroid belt, perturbed by Jupiter's gravity and the subtle radiation pressure of sunlight, until it settled into its current orbit, crossing the paths of Earth and Mars. That rubble pile is Ryugu. This means that Ryugu is not a primordial object in the strictest sense. It is a recycled one. Its individual grains and boulders are ancient, as old as the solar system itself. But their current arrangement is not. Ryugu was assembled from the wreckage of something larger, something older, something destroyed. It is a phoenix, a reconstruction, a second life built from the ashes of the first. And this raises a question that haunts the entire enterprise of asteroid science. When we study Ryugu, are we studying the original chemistry of the solar system, or are we studying chemistry that was scrambled, reshuffled, and reprocessed during the catastrophic disruption and gravitational reassembly of a larger body? The answer, frustratingly, is both. The individual grains retain their primordial chemistry, but their spatial arrangement, their proximity to one another, the way water flowed through the rock and created new minerals, all of that belongs to the parent body, not to Ryugu. Ryugu is a collage, a mosaic made of ancient tiles, arranged in a pattern that is not itself ancient. Disentangling these histories, separating the chemistry of the original nebula from the chemistry imposed by the parent body from the chemistry altered by Ryugu's own thermal evolution near the Sun, became one of the central challenges of Ryugu sample science. And it is a challenge that, as of the latest published analyses, has not been fully resolved. The data is dense, layered, and occasionally contradictory. Some measurements suggest extensive aqueous alteration in a water-rich environment, Others suggest that the water was limited, localized, and brief. Some grains show evidence of heating to several hundred degrees Celsius. Others appear never to have been warmed above room temperature. Ryugu's dust is not telling one story, it is telling many, and part of the scientific work, the painstaking, years-long effort that is still ongoing, involves figuring out which stories are compatible and which are in conflict. But here is what makes this truly terrifying. If the amino acids, the water, and the organic molecules found in Ryugu are representative of C-type asteroids generally, and there is good reason to believe they are, since C-types are by far the most common class of asteroid in the solar system, then the ingredients of life are not rare. They are everywhere. Every dark, carbon-rich asteroid drifting through the belt, every carbonaceous body lurking in the outer solar system, every tiny grain of interplanetary dust falling invisibly into Earth's atmosphere at a rate of roughly 40,000 tons per year. All of it carries the same molecular toolkit. Amino acids, water, organic complexity. The universe is not sterile, it is saturated with the precursors of biology. And if that is true, then the question is no longer whether life could have started on Earth. The question is whether life could have been prevented from starting. The ingredients were delivered, the water was provided, the chemistry was primed. On a warm, wet, geologically active world with a magnetic field to shield it from radiation and a thick atmosphere to moderate its temperature. A world like Earth. The emergence of life may not have been a miracle. It may have been inevitable. That is the terrifying implication of 5.4 grams of dust from a rock named after a mythical underwater palace. And scientists are only beginning to understand what it means. There was one more discovery that deepened the mystery further. Among the organic molecules identified in Ryugu's samples was uracil, one of the 4 nucleobases that make up ribonucleic acid, or RNA. RNA is the molecule that many scientists believe preceded DNA in the earliest forms of life on Earth. It can store genetic information, catalyze chemical reactions, and replicate itself, all functions that are necessary for life as we understand it. Finding uracil in an asteroid's dust was not simply finding a building block. It was finding one of the 4 letters of the genetic alphabet, written in stone that predates all biology. Alongside uracil, scientists found niacin, also known as vitamin B3, a molecule essential for metabolism in virtually every living organism on Earth. These were not trivial detections. They were specific, biologically meaningful molecules, found in concentrations consistent with formation in a low-temperature, water-rich environment, exactly the conditions believed to have existed inside Ryugu's parent body billions of years ago. The picture emerging from the data was radical. The early solar system was not just sprinkled with random organic chemistry, it was equipped with a specific molecular toolkit, amino acids, nucleobases, vitamins, water, arranged in patterns that eerily foreshadowed the chemistry of biology. As Hiroshi Naraoka of Kyushu University, the lead author of one of the initial studies on Ryugu's organics, said in an interview after the results were published, these molecules were waiting in space before the Earth was even born. They are the starter kit of life. Something is wrong with our assumptions. The old boundary between chemistry and biology, the clean dividing line that separated the living from the non-living, is not as sharp as we once believed. Ryugu's dust blurs that line, and it forces us to confront a possibility that is as exhilarating as it is unsettling. The cosmos does not merely permit life, it prepares for it. The capsule that carried Ryugu's samples back to Earth was small enough to hold in your arms. It measured roughly 40 centimeters in diameter, about the size of a large mixing bowl. It weighed roughly 16 kilograms, and it entered Earth's atmosphere on December 5, 2020, at a speed of roughly 12 kilometers per second, faster than any bullet, faster than any missile, faster than any naturally occurring object that strikes our planet, except for certain classes of high-speed meteorites. At that velocity, the air in front of the capsule was compressed so violently that it reached temperatures exceeding 10,000 degrees Celsius, hotter than the surface of the sun. A fireball streaked across the pre-dawn sky above the Australian outback, visible for hundreds of kilometers, and for a few seconds, anyone looking up from the red desert below would have seen what appeared to be a small, impossibly bright star descending at an angle toward the horizon. The heat shield held. It was made of carbon phenolic composite, designed to ablate, to deliberately burn away, carrying the thermal energy with it in a controlled sacrifice that protected the sample container inside. At an altitude of roughly 10 kilometers, the capsule's parachute deployed, and the fireball became a gentle descent. Minutes later, the capsule landed in the Woomera Prohibited Area, a vast military testing ground in South Australia that had been used as a recovery zone for Hayabusa missions before. Recovery teams located the capsule within hours, guided by a radio beacon and GPS coordinates. When they opened the outer shell and inspected the sealed sample containers inside, they found no breach, no contamination. The seal was intact. The samples from Ryugu, grains of dust collected 300 million kilometers away from two separate locations on an asteroid, one of them from beneath an artificially created crater, were inside, untouched by Earth's atmosphere. For the first time in history, a truly pristine sample of a C-type asteroid was in human hands, and then the real work began. The sample curation facility at JAXA's Institute of Space and Astronautical Science in Sagamihara was the most carefully controlled laboratory environment on the planet. The samples would be handled entirely within a glove box filled with purified nitrogen gas, a chemically inert atmosphere that would prevent any contact with oxygen, water vapor, or airborne organic contaminants. Every tool, every surface, every container had been sterilized and verified. The protocols had been developed over years, refined through practice runs with simulated materials, and tested against every conceivable source of contamination. When the sample container was finally opened, on December 14, 2020, the scientists were looking at material that had last been exposed to open space more than a year earlier, and before that, had been sealed inside an asteroid for 4.5 billion years. The first thing they noticed was the color. The grains were black, not dark gray, not charcoal, black. So black that under normal lighting, they absorbed almost all the light that fell on them, appearing as tiny voids against the white background of the sample dish. The largest fragments were a few millimeters across, about the size of a coarse grain of sand. The smallest were microscopic, visible only under magnification. The total mass recovered from both touchdowns was 5.4 grams, roughly the weight of a single sheet of paper. 5.4 grams does not sound like much, but in the economy of extraterrestrial sample science, it was a fortune. The Apollo missions returned 382 kilograms of lunar rock. The Genesis mission, which collected solar wind particles, brought back micrograms. The Stardust mission, which captured grains from the coma of Comet Wild 2, returned less than a milligram. Hayabusa 1's return from Itokawa yielded a few hundred individual grains. By comparison, Ryugu's 5.4 grams was an embarrassment of riches, enough material to supply research teams around the world for decades. And that is exactly what happened. JAXA divided the samples into portions and distributed them to 6 initial analysis teams, each focused on a different aspect of the material's properties. One team examined the mineralogy, the crystal structures of the rock. Another analyzed the organic chemistry, the carbon-bearing molecules. A third measured isotopic ratios, the atomic fingerprints that reveal where and when the material formed. A fourth studied the physical properties, the density, porosity, and mechanical strength of the grains. A fifth focused on volatile elements, gases trapped inside the rock, and a sixth performed a comprehensive bulk chemical analysis, measuring the abundances of every element in the periodic table present in the samples. The results arrived in waves, each one more surprising than the last. Before diving into what the analysis teams found, it is worth pausing to appreciate the scale of the analytical challenge they faced. Ryugu's grains were tiny. Most were less than a millimeter across. Many were fragile, porous, loosely bound aggregates that could crumble under gentle handling, and each grain was a composite of dozens of distinct mineral phases and organic compounds, intimately mixed at scales far below the resolution of the human eye. Analyzing such material requires instruments capable of resolving features at the nanometer scale, billionths of a meter, and detecting elements and molecules at concentrations of parts per million or even parts per billion. The analytical campaign employed some of the most powerful instruments in existence: synchrotron X-ray diffraction, scanning and transmission electron microscopy, secondary ion mass spectrometry, gas chromatography mass spectrometry, Raman spectroscopy, and dozens of other techniques, each targeting a different aspect of the material's composition, structure, or history. The coordination required was immense. JAXA allocated specific grain fractions to specific teams, ensuring that each analytical technique was applied to material from both touchdowns. Cross-contamination protocols were obsessively maintained. Chain of custody documentation rivaled that of criminal forensics. Every subsample was photographed, weighed, catalogued, and tracked through every step of preparation and analysis. The entire process was designed to ensure that the results would be reproducible, defensible, and free from any suspicion of contamination or error. The mineralogy team, led by researchers at Tohoku University, published their findings in the journal Science in June of 2022. They reported that Ryugu's samples were dominated by phyllosilicates, clay-like minerals formed by the interaction of rock and liquid water. The specific minerals identified, serpentine, saponite, and dolomite, were consistent with aqueous alteration at temperatures between roughly 0 and 150 degrees Celsius. The samples also contained magnetite, an iron oxide mineral that, on Earth, is sometimes produced by bacteria. In Ryugu's case, the magnetite was abiotic, formed by inorganic chemical reactions in a water-rich environment. But its presence added another layer to the growing picture of Ryugu's parent body as a wet, chemically active world. A world where the conditions for the emergence of life might have existed, if only for a geological moment. The math is striking. Ryugu's parent body formed roughly 2 to 4 million years after the birth of the solar system, a blink of an eye in cosmic terms. During that narrow window, the heat from decaying aluminum-26 warmed the interior enough to melt water ice, creating a network of fluid-filled pores and fractures. Water flowed through rock, minerals dissolved and reprecipitated, new crystals grew, chemical equilibria shifted, and then, as the radioactive heating faded and the body cooled, the water froze again, and the chemistry stopped. The entire episode of aqueous alteration lasted perhaps 10 million years, a geological heartbeat. And yet, in that heartbeat, the chemistry of life's building blocks was established. The organic chemistry team revealed something equally remarkable. Led by Hiroshi Naraoka at Kyushu University, the analysis identified thousands of distinct organic compounds in Ryugu's dust. Not dozens, not hundreds. Thousands. The molecular diversity was staggering, far greater than anything found in even the most chemically complex meteorites. Among the identified compounds were amino acids, amines, carboxylic acids, polycyclic aromatic hydrocarbons, nitrogen-bearing heterocyclic molecules, and aliphatic hydrocarbons. Some of these molecules were familiar to biochemists. Others had never been seen in any natural sample, terrestrial or extraterrestrial. The amino acid analysis deserves special attention, because it addresses one of the most provocative questions in the origin of life, the problem of chirality. Amino acids come in two mirror image forms called left-handed and right-handed, or L&D in scientific notation. On Earth, life uses almost exclusively left-handed amino acids. This is one of the deepest mysteries in biology. There is no known chemical reason why left-handed amino acids should be preferred over right-handed ones. Both forms are equally stable, equally reactive, equally capable of building proteins. And yet, from the simplest bacterium to the most complex animal, earthly life has chosen one and rejected the other. If the amino acids in Ryugu's dust showed a left-handed excess, a bias toward L-amino acids, similar to what we see in biology, it would suggest that the chiral preference of life did not originate on Earth. It would suggest that the bias was already present in the raw materials delivered from space, and that, in turn, would imply that the handedness of life is not an arbitrary accident, but a consequence of some physical process in the interstellar medium. Perhaps circularly polarized ultraviolet light from a nearby massive star, preferentially destroying one mirror form over the other. The initial results from Ryugu were tantalizing but inconclusive. Some amino acids showed a very slight excess of left-handed forms. Others showed no significant preference. The sample sizes were small, the concentrations low, and the statistical uncertainties large. The question of whether Ryugu's amino acids carry a chiral bias remains open, one of the most important unresolved questions in the entire field of astrobiology. Further analyses, using more material and more sensitive techniques, are expected over the coming years. The answer, when it comes, could reshape our understanding of why life on Earth looks the way it does. While JAXA's teams were dissecting Ryugu's dust grain by grain, another spacecraft was conducting a remarkably parallel mission on the other side of the solar system. NASA's OSIRIS-REx, origins, spectral interpretation, resource identification, and security regolith explorer, had been launched in September of 2016, 2 years after Hayabusa 2, and was bound for a different C-type asteroid, Bennu. Bennu is in many ways Ryugu's cousin. It is roughly the same size, about 490 meters in diameter, compared to Ryugu's 870. It has a similar spinning top shape, with an equatorial ridge and a boulder-strewn surface. Its spectral classification marks it as a B-type asteroid, closely related to C-types, carbon-rich, and expected to contain hydrated minerals and organic compounds. And like Ryugu, Bennu turned out to be far more challenging than anyone expected. When OSIRIS-REx arrived at Bennu in December of 2018, just months after Hayabusa 2 reached Ryugu, the mission team encountered the same nightmare that had confronted JAXA. Boulders, everywhere. The surface of Bennu was a dense, chaotic jumble of rocks, with no smooth terrain suitable for the spacecraft's sample collection mechanism, which was very different from Hayabusa 2's. OSIRIS-REx used a device called TAGSAM, touch-and-go sample acquisition mechanism, a long robotic arm with a circular collection head that would press against the surface and release a burst of nitrogen gas, stirring up loose material and capturing it in a filter. The search for a safe sampling site on Bennu took months. The team eventually settled on a small clearing called Nightingale, a shallow crater about 8 meters wide, roughly the size of a few parking spaces. On October 20th, 2020, just weeks before Hayabusa 2's sample capsule would return to Earth, OSIRIS-REx executed its own touchdown at Bennu. The TAGSAM head sank into the surface to a depth of nearly 50 centimeters, far deeper than expected, and the nitrogen gas blast stirred up a cloud of dark debris. The collection head was so full that its closure mechanism could not seal properly, and samples were visibly leaking out of the container during the ascent. The team made the decision to stow the head as quickly as possible to minimize loss. OSIRIS-REx departed Bennu in May of 2021 and delivered its sample capsule to Earth on September 24, 2023, landing in the Utah desert. The capsule contained roughly 250 grams of material, nearly 50 times more than Hayabusa 2 had collected. When NASA scientists opened it at the Johnson Space Center in Houston, they found a treasure trove of dark, fine-grained material, rich in clay minerals, sulfides, and organic compounds. Preliminary analyses confirmed the presence of hydrated phyllosilicates, magnetite, and sulfide minerals, a composition broadly similar to Ryugu's samples, but with important differences in detail. The comparison between Ryugu and Bennu became one of the most scientifically productive exercises in the history of planetary science. 2 asteroids, both C-type or near C-type, both rubble piles, both roughly diamond-shaped, both carbon-rich, yet their samples told subtly different stories. Bennu's material appeared to have experienced aqueous alteration at slightly different conditions than Ryugu's, with evidence of higher temperature mineral phases and possibly a longer duration of water-rock interaction. The organic molecules in Bennu's dust overlapped with, but were not identical to those found in Ryugu. The D/H ratios were similar in their overall range, but differed in the details of specific mineral fractions. These differences were exactly what scientists hoped for. A single sample from a single asteroid can tell you about one specific history. 2 samples from 2 different asteroids can tell you about a process. By comparing Ryugu and Bennu, researchers could begin to disentangle the effects of parent body size, orbital history, formation location, and thermal evolution on the chemistry of C-type asteroids. The goal was not to understand one rock, but to understand a population, the the billions of carbonaceous bodies that pepper the solar system, each one carrying its own archive of the pre-planetary past. The parallel between the two missions was itself a remarkable story of international scientific cooperation and friendly competition. JAXA and NASA had maintained close communication throughout both missions, sharing data, exchanging insights, and coordinating their analytical strategies. Scientists from each team served on the other's advisory boards. When Hayabusa 2's samples were returned first, NASA scientists were among the first outside Japan to receive allocated material for independent analysis. When OSIRIS-REx returned 3 years later, the favor was reciprocated. This cross-pollination ensured that both sets of samples were analyzed using the most diverse possible range of techniques and expertise, and that the conclusions drawn from each mission were independently validated by the other. The result was a golden age of small body science, a period of roughly 3 to 4 years, beginning in 2022, during which new findings from Ryugu and Bennu were being published almost weekly, each one adding detail to an increasingly complex and increasingly fascinating picture of the early solar system. The pace of discovery was exhilarating and, at times, overwhelming. Senior researchers described it as the most productive period in the history of cosmochemistry. The science of studying the chemical and isotopic composition of cosmic materials. But the comparison also raised new puzzles. One of the most striking was the difference in bulk density. Ryugu's density, measured by Hayabusa 2's orbital tracking, was roughly 1.2 grams per cubic centimeter, less dense than ordinary rock, slightly denser than water, and consistent with a porous rubble pile interior full of empty spaces. Bennu's density was even lower, about 1.19 grams per cubic centimeter. Both asteroids were mostly empty space. If you could somehow squeeze all the gaps out of Ryugu, compressing its material into a solid block, it would shrink to less than half its current volume. This porosity has implications that go beyond academic interest. A highly porous rubble pile responds to impacts very differently from a solid rock. When a projectile strikes a rubble pile, much of the impact energy is absorbed by the compression and rearrangement of internal voids, rather than being transmitted as a shock wave. The asteroid does not shatter cleanly. Instead, it absorbs the blow, deforms locally, and reconsolidates. This makes rubble pile asteroids surprisingly resilient against impacts, and paradoxically, very difficult to deflect or destroy if one of them were ever found to be on a collision course with Earth. This concern was not hypothetical. Both Ryugu and Bennu are classified as potentially hazardous asteroids, objects whose orbits bring them close enough to Earth to pose a conceivable impact threat over long timescales. Bennu, in particular, has a small but non-zero probability of impacting Earth in the late 2200s, a probability that orbital calculations have placed at roughly 1 in 2,800. If Bennu were to strike Earth, the energy released would be equivalent to roughly 1.4 billion tons of TNT, about 22 times the yield of the most powerful nuclear weapon ever detonated. The impact would not end civilization, but it would devastate a region the size of a small country. Understanding the internal structure of these objects, whether they are solid rocks, loose rubble, or something in between, is therefore not merely an academic exercise. It is a matter of planetary defense, and the data from Hayabusa 2 and OSIRIS-REx detailing the porosity, strength, and composition of these bodies in unprecedented detail is directly feeding into the models that will guide humanity's response if a threatening asteroid is ever detected. The numbers are striking. Before Hayabusa 2 and OSIRIS-REx, the internal structure of asteroids was inferred from models, simulations, and the study of meteorites. After these missions, scientists had direct measurements of surface strength, bulk density, grain-level composition, and impact response, all from bodies that represent the most common type of asteroid in the inner solar system. The leap in understanding was comparable to the difference between studying ocean currents from a satellite and actually dropping into the water to take a sample. Yet even with all this data, fundamental questions remained unanswered. The origin of the parent body, the larger asteroid from which both Ryugu and Bennu were likely derived, is still debated. Some models place the parent body's formation in the outer solar system, beyond the orbit of Jupiter, where temperatures were cold enough for water ice to be abundant and carbon-rich chemistry to proceed without interference from solar heating. In this scenario, the parent body was later scattered inward by Jupiter's gravitational perturbations, eventually entering the main asteroid belt between Mars and Jupiter, where it was destroyed by a collision. Other models suggest a formation location closer to the Sun, perhaps in the outer main belt itself, where conditions were cold but not as extreme as in the outer solar system. The distinction matters because it determines the initial inventory of volatile materials: water, carbon dioxide, methane, ammonia, available to drive aqueous alteration and organic chemistry. A parent body that formed beyond Jupiter would have started with more water ice and more carbon-rich ices than one that formed closer in, and the amount of water available directly determines the duration and intensity of aqueous alteration, which in turn determines the complexity of the organic molecules produced. The isotopic data from Ryugu samples has been used to argue both sides. Some oxygen isotope measurements align with an outer solar system origin. Others are more consistent with the main belt. The nitrogen isotope ratios are ambiguous. The carbon isotopes are complex, reflecting contributions from multiple sources: pre-solar grains, nebula gas, and aqueous alteration products that are difficult to deconvolve. As Shogo Tachibana, the principal investigator for Ryugu's sample analysis, noted in a presentation to the Lunar and Planetary Science Conference in 2023, Ryugu is telling us that the early solar system was more dynamic, more interconnected, and more chemically complex than any of our models predicted. We are not filling in the details of a known picture. We are discovering that the picture is different. That statement captures the essence of what Ryugu has done to planetary science. It has not confirmed existing theories. It has complicated them. It has shown that the neat, tidy story of asteroid formation and organic chemistry, a story refined over 50 years of meteorite analysis, was too simple. The reality is messier, richer, and more profound than the textbook suggested, and perhaps the most unsettling complication of all came from a finding that attracted less public attention than the amino acids or the water, but may ultimately prove more significant. Ryugu's samples contained carbonate minerals, specifically dolomite and brunnerite, formed by the reaction of carbon dioxide with magnesium and iron in the presence of liquid water. The carbon in these carbonates carried an unusual isotopic signature, a ratio of carbon-13 to carbon-12 that was significantly different from what had been measured in any meteorite. This is a puzzle because the isotopic composition of carbon is one of the most reliable tracers of the chemical conditions under which minerals form. A different isotopic ratio implies different conditions, different temperatures, different pressures, different concentrations of reactants than those assumed in standard models. Either the models of aqueous alteration inside Ryugu's parent body need to be revised, or the initial carbon inventory of the parent body was different from what has been assumed based on meteorite data. Either way, something is wrong with our assumptions, and resolving that discrepancy will require more data, more analysis, and more time. The full characterization of Ryugu's samples is expected to take decades. The 5.4 grams of material brought home by Hayabusa 2 will be studied by laboratories around the world for the rest of this century. Each new analytical technique, each new generation of instruments, each new theoretical framework will extract new information from those tiny grains. They are, in a very real sense, an inexhaustible archive, a library of the early solar system written in atoms, waiting to be read by instruments that have not yet been invented. There is another thread in the Ryugu story that deserves its own chapter: the question of magnetism. Before Hayabusa 2 arrived, some scientists hypothesized that C-type asteroids might preserve a record of ancient magnetic fields from the early solar system. The solar nebula, during its active phase, was threaded with magnetic fields generated by the young sun's powerful solar wind and by the turbulent motions of ionized gas within the disk. These fields could have been recorded in magnetic minerals, like magnetite, within the planetesimals and asteroids that formed during that era, much the way a tape recorder captures sound by magnetizing particles on a strip of tape. If Ryugu's magnetite grains carried a remnant magnetization, a frozen-in record of the magnetic field present when they formed, it would provide direct information about the strength and geometry of the solar nebula's magnetic field 4.5 billion years ago. That information, in turn, would constrain models of how gas was transported within the disk, how planets accreted material, and how the sun's early magnetic activity shaped the architecture of the entire solar system. The mascot lander carried a magnetometer specifically designed to measure any surface magnetic field on Ryugu. The results were sobering. Mascot detected no measurable magnetic field at the surface. The upper limit of the measurement was less than 1 nanotesla, roughly 1/50,000th of the strength of Earth's magnetic field. Ryugu was magnetically dead. This null result was paradoxically informative. It placed an upper limit on the strength of any ancient magnetic field recorded in Ryugu's minerals, and it ruled out models that predicted strong nebular magnetic fields at the distance from the Sun, where Ryugu's parent body formed. It also confirmed that Ryugu's parent body never developed an internal dynamo, a self-sustaining magnetic field generated by the convection of a molten metallic core, like Earth has. The parent body was too small, too cold, and too primitive to differentiate into layers of metal and rock. It remained an undifferentiated, chemically homogeneous mass, a condition that preserved its primordial chemistry, but denied it the internal dynamics that larger bodies develop. The magnetic data from Ryugu complemented a growing body of evidence from other missions and meteorite studies, suggesting that the early solar system's magnetic environment was more complex and more variable than simple models had assumed. The magnetic field was not uniform across the disk. It varied with distance from the Sun, with time, and with the local density and temperature of the gas. Mapping this variation requires data from multiple bodies at multiple distances, and Ryugu's contribution, though a null result, helped constrain the puzzle. There was yet another dimension to the Ryugu investigation that unfolded in parallel with the chemical and mineralogical analyses. The study of noble gases trapped within the samples. Noble gases, helium, neon, argon, krypton, xenon, are chemically inert. They do not form bonds with other elements under normal conditions, and yet they are found in tiny quantities inside the crystal lattices of certain minerals, implanted by the solar wind, or trapped during the condensation of grains from the nebular gas. The isotopic ratios of these noble gases serve as tracers of different processes. Solar wind implantation leaves a characteristic isotopic signature enriched in light isotopes like helium-3 and neon-20. Cosmic ray exposure, which occurs when a surface is unshielded in space, produces specific isotopes through spallation reactions, the shattering of atomic nuclei by high-energy particles. By measuring the amounts and ratios of different noble gas isotopes in Ryugu's samples, scientists could reconstruct the history of the material's exposure to solar radiation and cosmic rays, estimating how long it had been on or near the surface of the asteroid and how much processing it had undergone since formation. The results told a story of remarkable antiquity. Certain grains in Ryugu's surface samples showed solar wind implantation signatures consistent with exposure to the Sun for millions of years, as expected for material sitting on the surface of an airless body in the inner solar system. But the subsurface samples, the material collected near the artificial crater, showed dramatically lower solar wind signatures. These grains had been shielded. They had spent most of their history buried beneath the surface, protected from the Sun by overlying rubble. Their noble gas compositions were closer to the primordial values expected for material that had been sealed inside a parent body since the solar system's earliest days. This gradient, solar process material on the surface, pristine material below, was the clearest evidence yet that Hayabusa 2's dual sample strategy had worked exactly as intended. The first touchdown captured weathered surface material. The second touchdown, near the crater, captured deeper material that was closer to the original state. By comparing the two, scientists could quantify the effects of space weathering and strip them away, revealing the underlying chemistry of the parent body. The importance of this comparison cannot be overstated. For decades, asteroid scientists had debated whether the spectral properties measured by telescopes accurately reflected the true composition of asteroids. or whether space weathering had altered the surfaces so thoroughly that remote observations were misleading. Some researchers argued that C-type asteroids viewed through telescopes might look different from their meteorite counterparts because space weathering had changed their spectral fingerprints. Others argued that the discrepancies were due to sampling bias. The meteorites reaching Earth were not representative of the asteroid population as a whole. Ryugu's dual samples provided the first controlled test of these hypotheses. By comparing a weathered surface sample with a relatively unweathered subsurface sample from the same body, scientists could measure exactly how much space weathering changed the observable properties of a C-type asteroid. The answer was that space weathering did alter the spectral properties, making the surface appear slightly darker and spectrally redder. But the changes were moderate, not transformative. The fundamental compositional signature remained recognizable. This was good news for remote observers. It meant that telescopic classifications of asteroids, while not perfectly accurate, were at least broadly correct. The C-type label applied to Ryugu based on decades of telescopic observation was confirmed by direct sample analysis. The classification system worked. The cosmic ray exposure age, the time the material had spent within about a meter of the surface, exposed to galactic cosmic rays, was estimated at roughly 5 million years for the surface grains. This implied that Ryugu's surface was relatively young in geological terms, consistent with a rubble pile structure that periodically reshuffles its surface material through impacts, thermal cycling, and the slow outward migration of material driven by centrifugal effects from the asteroid's rotation. 5 million years. On a body that is 4.5 billion years old, the surface is being refreshed on timescales that are less than 0.1% of its total age. Ryugu is not static. It is slowly, subtly, continuously evolving, rearranging its rubble, burying old surfaces, exposing new ones, like a pile of sand perpetually stirred by invisible hands. This has implications for the broader understanding of asteroid surfaces. Many telescopic observations of asteroids rely on surface properties, reflectivity, spectral absorption features, thermal inertia, to infer composition. But if asteroid surfaces are constantly being renewed by internal reshuffling, then the surface may not represent the bulk composition at any given time. A C-type asteroid that appears spectrally bland from a telescope might be hiding a rich chemical interior beneath a weathered, depleted skin. The diversity of asteroid compositions inferred from telescopic surveys might be systematically biased, underestimating the chemical richness of these bodies by studying only their outermost layers. Ryugu taught us to look deeper, literally, and Hayabusa 2's story did not end when its sample capsule fell to Earth. In a move that exemplified the mission's extraordinary efficiency, JAXA redirected the spacecraft, which still had fuel and functional instruments, toward a new target. After releasing its sample capsule toward Earth in December of 2020, the main spacecraft performed a flyby of Earth without entering orbit and used the planet's gravity to redirect itself toward a small, fast-rotating asteroid designated 1998 KY26. This tiny body, just about 30 meters in diameter, is one of the fastest spinning asteroids known, completing a full rotation in roughly 10.5 minutes. Hayabusa 2 is expected to arrive at this object in July of 2031, making it one of the longest duration interplanetary missions in history. The extended mission, called Hayabusa 2 Extended, is focused on studying how very small, rapidly rotating asteroids maintain their structure. At such high spin rates, centrifugal forces at the equator exceed gravitational attraction. Material on the surface should be flung off into space, and yet the asteroid persists. Something is holding it together. That something is likely cohesive forces between grains, van der Waals forces, electrostatic attraction, or perhaps something else entirely. Understanding these forces is critical for planetary defense, because many potentially hazardous near-Earth objects are small, fast-spinning bodies, and knowing what holds them together determines what might break them apart if they threaten Earth. But the extended mission also serves a symbolic purpose. It demonstrates that sample return missions are not endpoints. They are inflection points. The spacecraft that carries the sample is itself a reusable scientific asset. capable of visiting multiple bodies, conducting multiple investigations, and accumulating data across a span of decades. Hayabusa 2, designed for a 6-year primary mission, may ultimately operate for 17 years or more, visiting two entirely different classes of asteroid and contributing to science long after its original mission objectives were achieved. This philosophy of mission extension and reuse is becoming central to the next generation of small-body exploration. JAXA is already developing concepts for follow-on missions that build on Hayabusa 2's heritage. The Martian Moons Exploration Mission, MMX, aims to visit the Martian moons Phobos and Deimos, collect samples from Phobos, and return them to Earth by the early 2030s. Phobos is widely suspected to be a captured asteroid, possibly a D-type body from the outer solar system, and its samples could reveal the composition of a class of primitive material even more ancient and less processed than Ryugu's. Meanwhile, NASA is leveraging the OSIRIS-REx spacecraft, now renamed OSIRIS-APEX, for an extended mission to the asteroid Apophis, which will make an extraordinarily close approach to Earth. In April of 2029, passing within roughly 32,000 kilometers of the surface, closer than the orbits of geostationary communication satellites, OSIRIS-APEX will rendezvous with Apophis shortly after this close approach and study how the gravitational tidal forces of the encounter alter the asteroid's spin, shape, and surface. It will not collect a sample, but it will provide data on the mechanical response of a rubble pile asteroid to extreme gravitational stress, data that directly complements the knowledge gained from Ryugu. And beyond these near-term missions, a more ambitious vision is taking shape. The concept of asteroid mining, extracting water, metals, and organic compounds from near-Earth asteroids for use in space, has moved from science fiction to engineering study. Companies and space agencies are conducting feasibility analyses for missions that would process asteroid material in situ, using solar energy to extract water for rocket fuel, metals for construction, and carbon compounds for manufacturing. Ryugu's data is feeding directly into these studies. The porosity, density, composition, and mechanical strength measurements from Hayabusa 2 are being used to design extraction systems and estimate the economic viability of mining operations. If asteroid mining becomes a reality, and many in the space industry believe it will within the next few decades, then Ryugu will have played a foundational role, not just in science, but in the economic development of the solar system. The humble rubble pile, studied for its primordial chemistry, may also prove to be a prototype for the resources that sustain humanity's expansion beyond Earth. But for now, the primary legacy of the Ryugu investigation remains scientific, and the science is still unfolding. New papers are published regularly, each one adding a piece to a puzzle that is far from complete. In 2024, a team reported the detection of previously unknown sulfur-bearing organic compounds in Ryugu's samples, molecules that may play a role in prebiotic chemistry by stabilizing amino acid structures in the presence of ultraviolet radiation. Another group identified traces of trapped nitrogen gas within magnetite crystals, suggesting that nitrogen cycling, a process critical to biology on Earth, had analogues in the chemical environment of Ryugu's parent body. Each discovery opens new questions. Each answer reveals a deeper layer of complexity. The 5.4 grams of dust sitting in clean rooms in Japan, in Houston, in laboratories across Europe and Asia are not inert samples. They are active participants in an ongoing dialogue between humanity and its origins, a conversation conducted in the language of isotopes and crystal structures and molecular bonds, a conversation that will continue for as long as there are scientists curious enough to listen. Take a breath. Step back from the data. Step back from the spectrometers and the isotopic ratios and the mineralogical maps. Step back from the spacecraft and the missions and the engineering triumphs. Step back from all of it and ask a simple question. What does this actually mean? Not for science, not for planetary defense or astrobiology funding or the next generation of sample return missions. What does it mean for you, listening to this in the dark, 3 billion kilometers from the nearest asteroid, on a planet made of the same dust that Ryugu is made of? Here is the deeper truth that emerges from Ryugu's 5.4 grams of ancient black dust. and it is a truth so large that the human mind struggles to hold it all at once. You are made of asteroid material, not metaphorically, not as a poetic gesture toward our shared cosmic origins. Literally, the water in your cells, the water that accounts for roughly 60% of your body mass, carries the same deuterium to hydrogen ratio as the water locked inside Ryugu's minerals. The amino acids in your proteins are the same amino acids found in the dust of a spinning top-shaped rubble pile between Earth and Mars. The nucleobases in your RNA are the same molecules sitting in grains that have been drifting through the void since before this planet existed. You are not separate from the asteroid. You are the asteroid, 4.5 billion years later, rearranged into a form that can think about where it came from. Let that sink in. Every origin story humanity has ever told, every creation myth, every cosmology, every scientific model of abiogenesis has placed a boundary between us and the rest of the cosmos. Here is Earth, where life happens. Out there is space, where it does not. Ryugu erases that boundary. The chemistry of life is not confined to our planet. It is a feature of the solar system, perhaps of the universe. The same processes that built amino acids on a frozen dust grain in the pre-solar nebula are the same processes that, billions of years later, built the muscles in your hands and the neurons firing in your brain as you listen to these words. There is no dividing line between living chemistry and non-living chemistry. There is only chemistry, an unbroken chain of molecular interactions stretching from the collapse of a molecular cloud to the emergence of consciousness. Ryugu's dust is a link in that chain, an early link, a foundational one, but a link nonetheless. This is not science fiction. This is chemistry confirmed by direct measurement of material returned from another world. Consider the timeline. 4.6 billion years ago, a cloud of gas and dust begins to collapse. Within it, ice-coated grains carry the seeds of organic chemistry, molecules formed by ultraviolet radiation in the cold dark of interstellar space. The cloud becomes a disk. The disk becomes a system of worlds. One of those worlds, Earth, is positioned in the habitable zone, at a distance from the young sun where liquid water can exist on the surface. But the water does not come from Earth's own rocks. Much of it comes from the bombardment of asteroids and comets during the first billion years of the planet's existence. Those impactors carry water. They carry amino acids. They carry nucleobases. They carry the entire molecular toolkit required for the emergence of self-replicating chemistry. And then, somewhere on that young, wet, violent world, perhaps at a hydrothermal vent on the ocean floor, perhaps in a shallow tidal pool, perhaps in a porous rock saturated with mineral-rich water, something crosses a threshold. Non-living chemistry becomes living chemistry. Molecules that catalyze their own replication appear. Membranes form. Information is stored. Evolution begins. Was that crossing inevitable? Was it a matter of time, given the right conditions and the right ingredients? Or was it a staggering fluke, a 1 in a trillion accident that happened to occur on this planet and never anywhere else? Ryugu's samples do not answer that question directly, but they shift the balance of evidence in a direction that many scientists find deeply provocative. If the molecular toolkit of life is universal, if amino acids, nucleobases, and water are standard features of C-type asteroids, and C-type asteroids are the most common class of small body in the solar system, then the raw materials for life are being delivered to every rocky planet in every planetary system in the galaxy. Not just ours, all of them. The Milky Way contains roughly 100 billion stars. Current estimates suggest that most of those stars have at least one planet, and a significant fraction have planets in the habitable zone. If each of those planetary systems also has a population of carbon-rich asteroids, and there is no reason to think ours is unique in this regard, then the ingredients of life are raining down on potentially billions of worlds, billions of warm ponds, billions of hydrothermal vents, billions of opportunities for chemistry to cross the threshold into biology. We do not know how many of those opportunities succeed. We do not know whether life requires special conditions beyond the right chemistry, a magnetic field to shield against radiation, a large moon to stabilize axial tilt, a giant planet to deflect incoming debris. We do not know whether the leap from chemistry to biology is easy or hard, common or rare, deterministic or miraculous. Ryugu's dust tells us only about the starting conditions. It tells us that the ingredients are there. It does not tell us whether the recipe works. But here is what haunts the scientists who study this material. The recipe has worked at least once, here, on this planet, in this solar system, with these ingredients. And the ingredients are the same everywhere. As Humberto Campins, a planetary scientist at the University of Central Florida and a member of the OSIRIS-REx science team, put it in a public lecture after the Bennu samples were returned, we used to ask whether Earth was special because it had the ingredients for life. Ryugu and Bennu have shown us that those ingredients are common. The question now is whether Earth is special because of what it did with them. That question, what Earth did with the ingredients, is the question that will define astrobiology for the next century, and it is a question that could not have been asked with such precision, such specificity, such empirical grounding, without the 5.4 grams of dust brought home by a Japanese spacecraft from a small black asteroid named after a mythical underwater palace. But there is an even deeper layer to this story, one that most people never think about, one that concerns not the origin of life, but the persistence of it. Ryugu is a rubble pile. It was created by the catastrophic destruction of a larger body. Its parent was shattered, annihilated by a high-speed collision that reduced a world tens of kilometers across to a cloud of expanding debris. And yet, the organic molecules inside that parent body survived. They endured the destruction of their home. They were scattered, reassembled, baked by the sun, irradiated by cosmic rays, and bombarded by micrometeorites for billions of years. And when a Japanese spacecraft touched the surface and collected a sample, those molecules were still there. Damaged, degraded, diminished, but present. This is a testament to the resilience of organic chemistry. Life's building blocks are not as fragile as we once assumed. They can survive catastrophic disruption. They can survive reassembly. They can survive billions of years of exposure to the harshest environment in the known universe. The vacuum of interplanetary space, with its extreme temperature swings, its relentless radiation, and its utter absence of any protective atmosphere. If amino acids and nucleobases can survive the destruction of a world, then the reservoir of prebiotic chemistry in the solar system is not confined to intact parent bodies. It is spread across every fragment, every grain, every mote of dust that was ever part of a C-type asteroid or its parent. The molecular seeds of life are not locked away in a few privileged locations. They are scattered everywhere, in the asteroid belt, in near-Earth orbits, in the dust that falls invisibly through Earth's atmosphere every day, in the surfaces of the Moon and Mars, where micrometeorites have been accumulating for billions of years. Let that sink in. Mars, in particular, presents a haunting possibility. The red planet was warmer and wetter in its distant past. It had liquid water on its surface. It had a thicker atmosphere, and it was being bombarded by the same population of carbon-rich asteroids that was delivering organic molecules to Earth. If Mars received the same molecular toolkit, and there is every reason to believe it did, then the conditions for the emergence of life may have existed on Mars just as they existed on Earth, perhaps at the same time, perhaps from the same delivery system. The same cosmic rain of amino acids and water that seeded life on our planet may also have seeded Mars. Whether that seed took root is unknown. No definitive evidence of past or present life on Mars has been found, but the discovery that Ryugu's ingredients are so similar to Earth's biology makes the search for Martian life more urgent than ever. Because if life arose independently on two planets in the same solar system, using the same prebiotic chemistry delivered by the same class of our asteroids, then life is not a fluke, it is a law, a natural consequence of a universe that manufactures its own precursors and delivers them to every door. Consider the implications for the moons of the outer solar system as well. Europa, a moon of Jupiter, has a global ocean of liquid water beneath an ice shell. Enceladus, a moon of Saturn, has geysers of water vapor erupting from its south pole. Both worlds are believed to have hydrothermal activity on their ocean floors, the same kind of mineral-rich, energy-producing environment that some scientists believe gave rise to life on Earth. And both worlds have been subjected to the same rain of carbonaceous material, from comets, from interplanetary dust, and from the same population of C-type asteroids that delivered organic molecules to the inner solar system. The molecular toolkit is there, the water is there, the energy is there. 3 out of 3 conditions that Ryugu has shown us are necessary preconditions for prebiotic chemistry. If life exists on Europa or Enceladus, even in its simplest, most primitive form, it would confirm the most radical implication of Ryugu's samples. It would confirm that life is not an Earth-specific phenomenon, but a cosmic one. A natural, repeatable outcome of physics and chemistry operating under the right conditions. The discovery of even a single microbe beneath the ice of Europa would be the most profound scientific finding in human history. And Ryugu's dust, in its quiet way, has made that discovery seem less like a fantasy and more like a prediction. The universe, it seems, is not indifferent to life. It is in the business of making life possible. Whether it is also in the business of making life actual, that remains for now the greatest unanswered question in all of science. And it is a question that began to sharpen into focus on a cold December morning in 2020, when a small capsule fell from the sky over Australia, carrying inside it the molecular memory of a time before Earth, before the Sun, before any of this existed. There is one more dimension to the deeper truth of Ryugu that demands attention. It concerns not what was found, but what was not found. Because sometimes the absence of something is as informative as its presence. Despite the extraordinary chemical complexity of Ryugu's samples, thousands of organic compounds, dozens of amino acids, nucleobases, vitamins, there was no evidence of biology, no cells, no fossils, no biomolecules arranged in the specific information-rich sequences that characterize living systems. The chemistry was complex but random. The amino acids were present in both left-handed and right-handed forms, without the strong chiral preference that would indicate biological processing. The organic molecules were diverse but disorganized, a library of letters without sentences, without words, without grammar. This absence is crucial. It tells us that we are looking at a stage in the story before the protagonist has appeared. Ryugu's chemistry is the prelude to life, not life itself. It is the ingredients laid out on the counter before the cooking begins. And the gap between those ingredients and a living cell, the smallest, simplest, most primitive living cell, is vast, incomprehensibly vast. A single bacterium contains roughly 100,000 different proteins, each one a precisely folded chain of amino acids, each one performing a specific function in a coordinated molecular economy of staggering complexity. The distance between Ryugu's scattered amino acids and a functioning cell is the distance between a pile of bricks and a cathedral. We do not know how that distance was crossed. We do not know whether it required millions of years of patient chemistry or a single fortuitous event. We do not know whether it happened in a warm pond, a hydrothermal vent, an ice crystal, or a thin film of water on a clay mineral surface. The origin of life remains the deepest unsolved problem in biology, and Ryugu, for all its revelations, has not solved it, but it has done something just as important. It has shown us that the starting conditions for life are not exceptional. They are default. They are what the solar system produces automatically, without guidance, without intention, without any special arrangement. The universe generates the precursors of life the way a forest generates fallen leaves. Effortlessly, inevitably, as a natural consequence of the physics and chemistry that govern its behavior. And that changes the calculus. If the starting conditions are universal, then the probability of life arising somewhere, anywhere, in the cosmos increases dramatically. Even if the origin of life is extraordinarily improbable, even if the chance of chemistry crossing the threshold into biology on any given planet is 1 in a billion, the sheer number of planets with the right starting conditions may be so large that the emergence of life somewhere is essentially guaranteed. 1 in a billion times 100 billion star systems in the galaxy yields 100 instances of life in the Milky Way alone. 1 in a trillion still yields thousands of cases across the observable universe. The numbers are so large that even vanishingly small probabilities produce outcomes. This is not wishful thinking. This is arithmetic. And Ryugu's contribution to that arithmetic was to show that one of the key variables, the availability of prebiotic molecular ingredients, is not a bottleneck. It is a given. Whether we will ever detect that life, whether it exists in forms that emit detectable biosignatures, whether it is close enough for our instruments to reach, whether it persists long enough for its signals to coincide with our brief technological moment, these are questions for another century, but the foundation of the search has been laid. Grain by microscopic grain in a laboratory in Sagamihara by scientists holding the oldest material any human has ever touched. There is a particular kind of loneliness that comes with understanding the timescales involved. The pre-solar grains in Ryugu samples formed in the envelopes of dying stars that burned out 7 or 8 billion years ago, roughly twice the current age of the Sun. Those grains drifted through the interstellar medium for billions of years before being swept up into the collapse of our solar nebula. They spent another 4.5 billion years inside an asteroid and its parent body. And then, after all of that, after 9 or 10 billion years of silent transit through the darkness, they were picked up by a spacecraft, placed in a capsule, dropped through an atmosphere, and opened by human hands. The journey of those grains is older than the Earth, older than the Sun, older, in some cases, than the galaxy itself in its current form. They carry within them the fingerprints of stars that died before anything in our corner of the cosmos existed, and now they sit in a laboratory, under fluorescent lights, being studied by creatures who have existed for a few 100,000 years on a planet that has been habitable for a few billion. The mismatch in scale is almost unbearable. These grains have been traveling for longer than complex life has existed anywhere in the known universe. They predate every fossil, every extinction event, every geological era. They were ancient before the dinosaurs. They were ancient before the first cell divided. They were ancient before the water on Earth's surface had finished accumulating. And yet, here we are, studying them, understanding them, extracting from them information about the conditions that preceded our own existence. There is something deeply paradoxical about this. The youngest, most ephemeral things in the universe, human minds grasping the oldest, most enduring things in the universe, pre-solar grains. The container is more fragile than its contents. The reader is younger than the text. Tomoki Nakamura, a cosmochemist at Tohoku University, who led one of the primary analysis teams for Ryugu samples, described the experience of first examining the grains under an electron microscope. "I could see structures that formed around a star that died before our sun was born," he said. "I was looking at something that was older than anything I could point to in the sky. It was humbling in a way I cannot fully describe. That humility, the awareness that we are latecomers studying the work of processes far older and far larger than ourselves, is perhaps the most important emotional truth to emerge from the Ryugu mission. It is not a truth that can be captured in data or published in a journal. It is the kind of truth that sits quietly in the back of your mind at 3 in the morning, when the world is still and the sky is dark, and you are alone with the knowledge that everything you have ever known, every person, every civilization, every species, occupies an unimaginably thin sliver of time in a story that began long before any of it, and will continue long after all of it is gone. Ryugu does not care about us. It does not know we exist. It was tumbling through the dark for billions of years before our species evolved, and it will continue tumbling long after we are gone. The 5.4 grams of its dust sitting in a Japanese laboratory will outlast every person alive today, every building, every nation. Mineral grains do not age the way biological organisms do. They do not decay. They do not die. They simply persist, carrying their ancient chemistry forward through time, indifferent to the civilizations that rise and fall on the planet next door. And there is something strangely comforting in that, because it means that even if humanity does not survive, even if our species follows the path of every other species that has ever lived and eventually goes extinct, the raw materials of life will still be out there, drifting on asteroids, falling onto young planets, seeding the chemistry that might, somewhere, sometime, produce another intelligence capable of looking up at the sky and wondering where it came from. The story does not end with us. It does not even particularly depend on us. We are one expression of a chemical process that began before the sun ignited and will continue after the sun burns out. Ryugu's dust is a reminder that we are not the point of the story. We are a chapter, a beautiful, improbable, heartbreakingly brief chapter in a book that has been writing itself for 13.8 billion years and shows no signs of stopping. And perhaps that is the deepest truth of all. The universe is not waiting for life to appear. It has been preparing for it from the beginning. Every supernova that scattered heavy elements into the void was forging the ingredients. Every molecular cloud that condensed into a new planetary system was mixing the recipe. Every carbonaceous asteroid, drifting silently through the dark, is carrying the starter kit, sealed and preserved and ready to be delivered. We spend so much time searching for life beyond Earth, scanning radio frequencies, analyzing exoplanet atmospheres, designing probes to drill into the ice of Europa, that we sometimes forget what Ryugu has already shown us. The search for life's origins does not require us to look outward. It requires us to look down, at the ground beneath our feet, at the water in our cells, at the amino acids in our muscles, because all of it came from out there. Every molecule of water you have ever drunk was forged in a cloud of interstellar gas and delivered to this planet by rocks like Ryugu. Every protein in your body is built from amino acids that were first assembled on the surfaces of ice-coated dust grains 4.5 billion years ago, in a place so cold and so dark that even light struggled to reach. You are not observing the universe. You are the universe observing itself. And Ryugu's dust is the proof. This is not science fiction. This is the conclusion of one of the most meticulous, most rigorous, most carefully controlled scientific investigations ever conducted. A spacecraft traveled 300 million kilometers, touched an asteroid twice, blasted a crater into its surface, collected samples from 2 locations, and brought them home in a sealed capsule that was opened under nitrogen gas in a laboratory cleaner than an operating room. Every measurement has been checked, verified, reproduced, and peer-reviewed. The amino acids are real, the water isotopes match, the nucleobases are present, the pre-solar grains carry the fingerprints of dead stars. This is what 5.4 grams of dust from a rock called Ryugu have told us. And the story is far from over. Stand somewhere quiet tonight. Step outside if you can and look up. If the sky is clear, you will see stars, thousands of them, if you are far enough from city lights. Each one is a furnace, burning through its hydrogen fuel, forging heavier elements in its core. And one day, in 1,000,000 years, or 1 billion or 10 billion, each one will die. Some will fade gently into white dwarfs. Others will explode, scattering their guts across light years of empty space. And when they do, the elements they created, the carbon, the oxygen, the nitrogen, the silicon, the iron, will mix with the surrounding gas and dust, drift for eons through the interstellar void, and eventually be swept up into a new collapsing cloud, a new forming star, a new disk of debris, a new generation of worlds. That is what happened to create our solar system. That is what happened to create the atoms in Ryugu's dust. And that is what happened to create you. The journey from Ryugu's landing in a Japanese cleanroom to this moment, this breath, this thought, this heartbeat, is a single continuous thread. It stretches from the death of ancient stars, through the formation of pre-solar grains, through the condensation of the solar nebula, through the accretion of planetesimals, through the catastrophic destruction and gravitational reassembly of Ryugu's parent body, through 4.5 billion years of silent drift in the cold dark of interplanetary space, through a spacecraft launched from a small island off the coast of Japan, through 2 audacious touchdowns on a boulder-strewn surface in microgravity, through a capsule that blazed like a temporary star above the Australian desert, and into a laboratory where human hands made of the same atoms, the same amino acids, the same water, opened a container and stared at the oldest material anyone had ever touched. That thread is not metaphorical, it is chemical. The atoms in Ryugu's dust and the atoms in your body were forged in the same class of stellar processes, carried through the same molecular clouds, incorporated into the same solar nebula, and distributed among the same population of planetesimals. The only difference is that some of those atoms ended up in a rubble pile asteroid, and others ended up in a planet with liquid water, an atmosphere, and 4 billion years of biological evolution. What does this mean for the future? It means that every mission to a small body, Every asteroid flyby, every comet rendezvous, every sample return is an act of self-investigation. We are not studying foreign objects. We are studying the raw materials from which we ourselves were assembled. The distinction between studying space and studying the origin of life is a false one. They are the same investigation. Ryugu made this concrete. It put the evidence in our hands. It showed us, atom by atom, that the chemistry of life is the chemistry of the cosmos, expressed in a particular way on a particular world. It also means that our approach to searching for life beyond Earth must change. The old approach, look for habitable planets, look for biosignatures in their atmospheres, hope to find something recognizable, remains valid but incomplete. Ryugu has shown us that the prebiotic ingredients are delivered by asteroids. This means that the presence of a volatile-rich, carbon-bearing small body population around a star system is not just a nice-to-have. It may be a prerequisite for life. A planetary system without carbonaceous asteroids may lack the delivery mechanism that seeds its planets with the molecular toolkit of biology. The habitability of a planet depends not just on its own properties, but on the properties of the small body population surrounding it. This insight is already shaping the way astronomers evaluate the potential for life in exoplanetary systems. Debris disks, the rings of dust and rubble observed around many young stars, are now being scrutinized not just as markers of planetary formation, but as potential reservoirs of prebiotic chemistry. A thick debris disk, rich in carbon and water, may signal a planetary system with a generous supply of life's ingredients, constantly being delivered to its inner rocky planets by the same gravitational perturbations that shaped our own asteroid belt. There is also a philosophical dimension to Ryugu's legacy that resists quantification but demands acknowledgement. For all of recorded history, human beings have looked at the night sky and wondered whether we are alone. That question has motivated religions, inspired literature, and driven scientific inquiry. Ryugu does not answer the question, but it changes the nature of it. Before Ryugu, the question was framed by uncertainty about the starting conditions. Were the ingredients of life unique to Earth? Were they produced only under special circumstances? Was our planet's chemistry the result of a fortunate accident that might never be repeated? After Ryugu, those questions are largely settled. The ingredients are not unique. They are not rare. They are not the result of special circumstances. They are everywhere. Amino acids are everywhere. Water is everywhere. Nucleobases are everywhere. The question of whether we are alone is no longer a question about chemistry. It is a question about probability and time. Whether the chemistry of life, given sufficient time and sufficient opportunity, always crosses the threshold into biology, or whether that crossing is so improbable that it has happened only once. Here, on this world, in this solar system, we do not yet know the answer. We may never know with certainty. But Ryugu has narrowed the question to its sharpest, most essential form. And that narrowing, that reduction of a cosmic mystery to a precise, testable hypothesis, is perhaps the greatest gift that 5.4 grams of ancient dust has given us. The mission itself, the Hayabusa 2 mission, deserves reflection as an accomplishment of the human species, not merely of the Japanese Space Agency. Consider what it required. An international collaboration spanning decades of planning and development, engineering so precise that a spacecraft could navigate to a specific patch of an asteroid smaller than most sports stadiums, at a distance of 300 million kilometers, with a communication delay of 16 minutes, and touch the surface for less than 1 second without crashing. Science so careful that amino acids could be detected in concentrations of parts per billion, in a sample smaller than a teaspoon, without a single molecule of terrestrial contamination. Ambition so bold that the mission's designers included a plan to deliberately blow a hole in the asteroid and collect material from the resulting crater, a maneuver that had never been attempted and could have destroyed the spacecraft. Hayabusa 2 succeeded not because it was lucky, it succeeded because it was brilliant. And because, when things went wrong, when the surface was not what anyone expected, when the boulders made landing impossible, when the original mission plan had to be thrown away and rewritten in real time, the engineers and scientists rose to meet the challenge with creativity, persistence, and a willingness to take calculated risks that lesser missions would have refused. In the grand timeline of space exploration, Hayabusa 2 occupies a peculiar position. It is not as famous as the Apollo missions. It is not as photogenic as the Mars rovers. It does not carry the romantic narrative of human spaceflight. And yet, in terms of its scientific impact, the depth and breadth of knowledge gained, the fundamental questions addressed, the paradigms challenged and revised, it may ultimately prove more consequential than any of them. Because the question it addressed is not, can we send people to the moon, or is there water on Mars? The question it addressed is, where do we come from? And the answer it provided, we come from the dust of ancient rocks, delivered by the silent collisions of a young and violent solar system, is an answer that changes everything. Not immediately, not dramatically, not in the way a war or a pandemic or a technological revolution changes things, slowly, subtly, in the way that a new understanding of your own origins changes the way you see yourself in the mirror. You look the same, but you know something you did not know before. And that knowledge, once acquired, cannot be unacquired. It sits inside you, quietly reshaping the way you think about life, about the sky, about the water you drink, and the ground you stand on. Ryugu has given us that knowledge, and we are still learning how to carry it. There is one final reflection that seems fitting as this journey draws toward its close. The Hayabusa 2 mission was, at its core, a human response to cosmic indifference. The universe does not explain itself. It does not label its components or provide instructions. It simply exists, vast, silent, and completely unconcerned with whether any conscious being ever understands it. Against that indifference, a group of human beings spent more than a decade designing, building, launching, and operating a spacecraft to travel 300 million kilometers to a rock the size of a large building, touch it for less than a second, and bring back a pinch of dust. Not because the universe asked them to, not because survival demanded it, but because they wanted to know. That impulse, the desire to know, to understand, to see what has never been seen, is itself a product of the same cosmic chemistry that Ryugu carries inside its grains. The carbon in the neurons that conceived the mission is the same carbon found in Ryugu's organic molecules. The water in the blood of the engineers who built the spacecraft is isotopically similar to the water locked in Ryugu's phyllosilicates. The amino acids in the muscles of the scientists who analyzed the samples are the same amino acids found in the dust they were studying. In a very real sense, Ryugu's dust was studying itself. The universe, through the medium of human curiosity, was examining its own earliest materials. And in doing so, it was completing a circle that began 4.5 billion years ago, when a cloud of gas and dust collapsed and set in motion the chain of events that would produce, among countless other things, a species capable of sending machines to asteroids and asking what they are made of. That circle will not close, not fully, not in our lifetime. The questions that Ryugu has raised will take generations to answer, and each answer will raise new questions, and each question will demand new missions, new instruments, new theories. The dialogue between humanity and the cosmos is open-ended. It has no final page, no concluding chapter, but it has moments of extraordinary clarity. Moments when the data aligns, the pieces fit, and for a brief shining instant, the fog lifts and we see, clearly, unmistakably, what we are and where we come from. The Hayabusa 2 mission gave us one of those moments, and its light will not fade for a very long time. Somewhere between the orbits of Earth and Mars, a small, dark rock continues its slow tumble through the void. It is blacker than charcoal. It is roughly the shape of a diamond, with a sharp equatorial ridge and a surface covered in boulders that cast razor-edged shadows across terrain. So dark it seems to absorb not just light, but attention itself. It weighs roughly 450 million kilograms. It is 870 meters from one side to the other, and it is missing 5.4 grams. That is all Hayabusa 2 took. 5.4 grams, less than the weight of a nickel. A smudge of dark powder that, placed on a kitchen scale, would barely register. And yet that smudge contained a message that had been sealed inside stone for 4.5 billion years, carried across 300 million kilometers of empty space, and delivered to a species that had spent its entire existence wondering where it came from. The asteroid does not know what it gave us. It has no awareness of the laboratories in Sagamihara and Houston where its grains are being studied under electron microscopes. It has no knowledge of the scientific papers, the conferences, the late-night debates between researchers about what the data means. Ryugu is oblivious to the revolution it has caused. It continues its orbit, tumbling slowly, losing a few micrograms of surface material to every micrometeorite impact, warmed by the sun on its close approaches, and chilled to near absolute zero temperatures on its far swings. It is simply a rock, but a rock that happened to carry, in its darkest and most ancient grains, the chemical memory of a time when stars were dying and worlds were being born. The message was simple. Life's ingredients are not from Earth, they are from space. The water in your body was forged in a molecular cloud and delivered by ancient rocks. The amino acids in your cells are the same amino acids found on the surface of a rubble pile asteroid. The nucleobases in your RNA were first assembled on ice-coated dust grains in the darkest, coldest reaches of the pre-solar nebula. You are not a product of this planet alone. You are a product of the entire solar system. Its stars, its dust, its collisions, its chemistry, its 4.5 billion year campaign to turn dead matter into living things. Ryugu was not what we thought it was. We thought it was a rock, a target, a data point, an item on a mission manifest. Instead, it turned out to be a mirror pointed back at us, reflecting not our faces but our origins, showing us that the line between a rock in space and a human being is not a line at all. It is a spectrum, a gradient, a continuous transformation from simple to complex, from inert to alive, from dust to thought. If you could somehow compress the entire history of the solar system into a single year, if the birth of the sun happened at midnight on January 1st, and the present moment were midnight on December 31st, then the formation of Ryugu's parent body would have occurred in the first week of January. The catastrophic collision that shattered it and created Ryugu would have happened sometime in the spring. The emergence of life on Earth would have occurred around mid-March. Dinosaurs would not appear until late December. And humans, all of human history, every civilization, every war, every poem, every scientific discovery, would fit into the last fraction of a second before midnight on December 31st. In that compressed year, the Hayabusa 2 mission, the decades of planning, the years of flight, the seconds of surface contact, would be an event so brief it would not even register on a clock with a second hand. And yet, in that unimaginably brief moment, a species that had existed for an eye blink of cosmic time reached across 300 million kilometers of space, touched a fragment of the oldest material in the solar system, and brought a piece of it home. Why? Because we wanted to know. Because the question, where do we come from, is not optional for a species that has become aware of its own existence. Because the night sky demands answers, and we are the only things in the solar system capable of asking the questions. Ryugu gave us answers. Not all of them, not even most of them, but enough to change the story we tell ourselves about what we are, enough to know that the ingredients of life are not special, not local, not the result of a one-time accident on a single favored world. They are common. They are ancient. They are woven into the fabric of the cosmos with the same ubiquity and the same indifference as gravity or light. The universe makes the building blocks of life the way it makes everything else, through physics and chemistry, operating over time at every scale from atoms to galaxies. It does not intend to create life. It does not try. It simply follows its laws, and life is one of the things that those laws permit. Whether life is one of the things those laws require, whether the universe, given enough time and enough matter and enough energy, inevitably produces minds capable of understanding themselves. That is a question Ryugu cannot answer. It may be a question nothing can answer. It may be the question that defines the next 1,000 years of scientific inquiry, or the next million, or the entire remaining lifespan of our species. Think about the Hayabusa 2 spacecraft for a moment. Think about the audacity of it. A machine, built by mammals, on a planet orbiting an unremarkable star, launched itself across hundreds of millions of kilometers of vacuum, guided by equations written centuries ago by other mammals who never imagined their mathematics would be used this way. That machine found a rock smaller than most city blocks in the vastness of interplanetary space, matched its orbit, and hovered above it for more than a year. It dropped tiny rovers onto the surface. It fired an explosive device to create a crater. It descended twice to kiss the surface and steal a handful of dust. Then it flew home, dropped its cargo through the atmosphere inside a heat shield, and that cargo was caught by humans standing in a desert on the far side of the world from where it launched. All of this to answer one question: where do we come from? No other species in the history of this planet has asked that question. No other species has had the capacity to ask it. And the fact that we can, the fact that carbon and water and amino acids, after 4.5 billion years of rearrangement, have produced a creature capable of building a spacecraft to visit the very rocks that delivered those ingredients, is itself the most astonishing fact in this entire story. But for now, tonight, under whatever sky you are sleeping beneath, this much is certain. 5.4 grams of ancient black dust, collected from a small dark asteroid between the orbits of Earth and Mars, have told us that we are made of the same stuff as the stars, the same stuff as the asteroids, the same stuff as the cold, silent, unfathomably ancient cloud of gas and dust that collapsed to create everything we know. We are not visitors in this universe. We are its product, its expression, its attempt, if something without intention can be said to attempt to understand itself. And somewhere out there, tumbling in the dark, missing a pinch of its surface, a diamond-shaped ruin named after a mythical palace at the bottom of the sea continues its orbit. It does not know what it has told us. It does not know that a small machine once landed on its surface, stole a handful of its dust, and carried it home to a species that would spend decades deciphering its meaning. It does not know, but we do. And that knowledge, fragile, fleeting, confined to a thin layer of atmosphere on a small blue world, is, for the moment, the most extraordinary thing in the solar system. The rock does not care, the rock endures, and in the silence between the stars, the ingredients of life continue their ancient, patient, unending journey. From dust to dust, from star to star, from one world to the next, waiting for the next chance, carrying the code forever.